As you progress in your flying, you will probably be exposed to more sophisticated aircraft, and along with these sophisticated aircraft come advanced systems. For example, high-performance aircraft may be equipped with fuel injection systems, turbochargers, constant speed propellers, advanced environmental control systems, de-icing or anti-icing systems, and retractable landing gear. In this presentation, we'll look at these systems in detail and provide you with a basic understanding of each one. Since the specific operating procedures for each system vary from one manufacturer to another, you should always consult the pilot's operating handbook or aircraft flight manual prior to operating any unfamiliar system. In an effort to gain the maximum amount of power from small lightweight aircraft engines, manufacturers have devoted a great deal of engineering research to advanced fuel induction systems. One of the most successful of these is fuel injection. Unlike a carburetor which mixes fuel and air prior to reaching the intake manifold, a fuel injection system injects fuel into the intake port, where it is mixed with air just prior to entering the cylinder. This allows for an even distribution of fuel to the cylinders and a more uniform mixing of the fuel and air. Let's quickly look at the components of a typical fuel injection system. The first component that we'll look at is the auxiliary or boost pump, which is usually an electric pump and serves several purposes. Its primary function is to pressurize the injection system prior to engine start. This forces fuel through the lines. The auxiliary pump also maintains fuel pressure in the event the engine-driven pump fails. The next component is the engine-driven fuel pump. Once the engine is started, this pump pressurizes the system by taking fuel from the tanks and sending it to the fuel injector unit. In some systems, the fuel pump supplies more fuel than the injector unit needs. In this case, the excess fuel is routed back to the tank through a return line. In other systems, the fuel is strictly metered and no return line is required. After the fuel is pressurized by the fuel pump, it moves into the fuel injector unit. Here, valves meter the fuel according to the mixture setting and the flow of air into the engine. The metered fuel is then sent to the fuel flow divider, or fuel manifold, which is located on the top of the engine. It's designed to divide the fuel evenly between each of the fuel injection nozzles. Within the divider, there is a set of valves that automatically shuts off the flow of fuel to the engine when the mixture is placed in the idle cutoff position. After the metered fuel leaves the flow divider, it's injected into the engine through the injector nozzles located on each cylinder head. At this point, the fuel is mixed with the air in the induction manifold just outside the intake valves and combustion chamber. A fuel flow indicator, calibrated in pounds or gallons per hour, is connected to the outlet of the flow divider. It measures the pressure being applied to the discharge nozzles. Now that you're familiar with the basic components of a fuel injection system, let's look at some of the advantages fuel injection has over carburation. As mentioned earlier, one advantage of fuel injection is the even distribution of fuel to each cylinder. Let's look at why this is beneficial. On a conventional carburetor system, the metering and vaporization takes place at the beginning of the induction system. Notice how the center cylinder is closer to the carburetor than the cylinders at each end. This results in an uneven distribution of the fuel-air mixture. The ideal solution for this would be to have a carburetor at each cylinder. This is what a fuel injection system does. The injection nozzle acts just like a little carburetor, delivering equal amounts of fuel to all cylinders. This allows for a smoother running engine with more horsepower for the same amount of fuel. In addition, the engine will operate at lower temperatures. This decreases the chance of experiencing detonation or pre-ignition and increases engine life and reliability. Another advantage of fuel injection is that it is not susceptible to carburetor icing. Float-type carburetors are highly susceptible to icing due to where vaporization occurs. As intake air passes through the venturi, it cools. Further cooling occurs during the vaporization process. This drop in temperature can cause moisture to freeze and adhere to the internal parts of the carburetor. In a fuel injection system, there is no significant temperature drop across the throttle valve, so icing is unlikely. In addition, the fuel is vaporized at the cylinder head, where increased temperatures make icing virtually impossible. One place where ice can accumulate in a fuel injection system is on the air intake. If this happens, all air could be cut off to the engine, causing it to quit. To prevent this from happening, some induction systems have an alternate air door. When opened, air from inside the cowling is taken into the induction system. Although this allows the engine to keep running, the reduced airflow and increased temperature affects the amount of power the engine can produce, much like the effect carburetor heat has on a carbureted engine. Although it may sound like fuel injection is the perfect system, it does have some drawbacks, the most significant being the increased possibility of vapor lock. Vapor lock occurs when vaporized fuel blocks the flow of liquid fuel to the fuel injection system. The reason fuel injection systems are more likely to experience vapor lock is because there are more fuel lines in close proximity to the engine and the heat it produces. If temperatures are hot enough, the fuel inside the lines vaporizes, resulting in low fuel pressure or engine failure due to fuel starvation. Fuel-injected airplanes that are flown frequently with only short stops between flights are highly susceptible to vapor lock. This is because some of the heat given off by the engine is absorbed by the fuel lines, causing the fuel to vaporize. Vapor lock can usually be remedied by turning on the auxiliary fuel pump and forcing cooler fuel through the system. The last topic we'll discuss is starting procedures. Although the starting procedures vary between manufacturers of fuel-injected engines, all of them have one thing in common. That is, if the engine is cool to the touch or is being started for the first flight of the day, the system will have to be primed. This is accomplished with the auxiliary fuel pump. With the throttle and mixture set according to the POH, turn on the electric fuel pump and monitor the fuel flow indicator. When a sufficient fuel flow rate is noted, continue with the specified starting procedures. A common area of difficulty with fuel injection is starting a hot engine. As mentioned earlier, hot engines cause fuel in the fuel lines to vaporize. Again, the auxiliary fuel pump is used to purge the system of the vapor lock. When doing this, you want to make sure you follow the manufacturer's procedures to reduce the chance of flooding the engine and possibly starting a fire.
Another aircraft system that helps increase performance is turbocharging. Let's take a look at how turbocharging works and discuss some of the unique characteristics of operating an aircraft that is equipped with a turbocharging system. As you know, when you climb, the ambient air pressure decreases approximately 1 inch of mercury for every 1,000 feet. What this means is that there is less air available for combustion at higher altitudes. Because of this, normally aspirated engines are not able to produce maximum manifold pressure with an increase in altitude. In order for a reciprocating engine to overcome this problem, turbochargers were installed as a means of getting more air into the engine. With a turbocharger, intake air is compressed before it enters the combustion chamber. This allows the engine to obtain higher manifold pressures, which equate to increased engine output. To better understand how a turbocharger works, let's take a brief look at the components of a typical system. There are 3 components that are common to all turbocharging systems. They are the compressor, the turbine, and the wastegate. As air enters the intake, it passes through a compressor where it is compressed by the centrifugal force created by the impeller blades. The compressed air is then routed from the ring surrounding the impeller through the throttle body to the cylinder. The compressor is driven by a turbine which is propelled by the engine's exhaust. If all of the exhaust from the engine were allowed to pass through the turbine at low altitudes, the compressor would produce excessive manifold pressure and high operating temperatures. To alleviate this possibility, a wastegate is added to the system to control the amount of exhaust gas that is routed through the turbine. When the wastegate is open, most of the exhaust bypasses the turbine. In this situation, the engine operates much like a normally aspirated engine. When the wastegate is closed, all of the exhaust gas is used to spin the turbine. In this case, the maximum amount of compressed air is being delivered to the manifold. In some turbocharged engines, the wastegate is controlled by a pressure-sensing controller mechanism and a wastegate actuator. Once the manifold pressure is set on this type of system, the wastegate position adjusts automatically to maintain the desired power output. On less complex systems, the position of the wastegate is regulated by throttle movement. When the throttle is moved forward, the wastegate moves to the closed position. When operating this type of system, you must give close attention to throttle operations since excessive manifold pressures can be produced at low altitudes. For specific operating procedures on the turbocharging system you're using, consult the pilot's operating handbook or aircraft flight manual. An area you need to be familiar with before operating a turbocharged engine is critical altitude. This occurs when the wastegate is completely closed and the turbine is spinning at its highest speed. Once the critical altitude is reached, manifold pressure will decrease with an increase in altitude, just like a normally aspirated engine. Another concern for turbocharged engines is the shutdown procedure. After a flight, the turbine may still be spinning at several thousand RPM. When you shut the engine down, the oil supply to the turbine is cut off. Therefore, before shutting the engine down, allow the turbine a chance to spool down with oil being supplied to it by idling the engine for the time specified by the manufacturer. When you get into a high-performance aircraft for the first time, one of the differences you'll probably notice is the propeller pitch control next to the throttle. As you will soon learn, this control is used to vary the propeller blade angle to gain additional performance and efficiency from small, lightweight aircraft engines. Before we get into the mechanics of constant speed propellers, let's quickly examine why they are more efficient than fixed-pitch propellers. Thrust is a product of engine horsepower and propeller efficiency. If a propeller could operate at 100% efficiency, all of the engine's power would be converted into thrust. However, no propeller can attain 100% efficiency. Moreover, a fixed-pitch propeller produces its maximum thrust only at a specific RPM and airspeed. For example, a propeller with a low blade angle is very efficient at low air speeds, such as during takeoffs and landings, but its efficiency decreases rapidly as speed increases. Whereas a propeller with a high blade angle is more efficient at cruise speed. Fixed-pitch propellers can be designed either with low blade angles to produce optimum takeoff and climb performance, with high blade angles for optimum cruise performance and fuel economy, or as a compromise between the two. On aircraft equipped with constant speed propellers, the propeller can be adjusted to maintain the optimum pitch angle. Thus, constant speed propellers can maintain a high level of efficiency over a wide range of airspeeds. Before we get into the operational considerations of constant speed propellers, let's briefly examine the components of a typical system. These include the throttle, the propeller, or prop control, the governor, and the propeller itself. Unlike the throttle, which controls RPM on an aircraft with a fixed-pitch propeller, the throttle on an aircraft with a constant speed propeller controls manifold pressure. The manifold pressure gauge is usually located near the tachometer and is sometimes combined with the fuel flow indicator. Since the amount of power that an engine produces is directly related to the fuel airflow, manifold pressure increases as you move the throttle forward and decreases as you move it back. The prop control is used to set the propeller RPM by changing the pitch of the propeller. When the prop control is full forward, the propeller blades are at their lowest pitch angle and produce the highest RPM. When the prop control is pulled aft, the propeller blades move to a higher pitch, resulting in a lower RPM. The prop control is connected to a governor, which is located on the front of the engine. The basic governor contains an oil pump, a valve, flyweights, and a spring. The governor maintains a specific RPM by directing oil to or releasing oil from the propeller hub to adjust the blade angle. The propeller hub houses the propeller blades, which rotate on a set of bearings, and a piston, which when pushed by oil, causes the blades to rotate to a higher pitch. When oil is released from the hub, aerodynamic forces acting on the blades of the propeller will twist the blades to a low pitch. Now that you're familiar with the components of a constant speed propeller, let's take a moment to examine how these components work to control a propeller's pitch. When you set the prop control, you're actually setting the spring tension in the governor to maintain a desired RPM. With the tension set, the system remains in a state of equilibrium until the aircraft accelerates or decelerates. When your airspeed increases, the propeller RPM also increases, which in turn increases the centrifugal force acting on the flyweights. This causes them to tilt outward, putting more tension on the spring and raising the valve. With the valve in this position, boosted oil is routed to the propeller hub. Once the oil reaches the propeller hub, it pushes the hydraulic piston rearward and increases the blade angle. This reduces RPM until the centrifugal force on the flyweights decreases and allows the valve to return to the neutral position. Conversely, when your airspeed decreases, propeller RPM decreases. This causes the flyweights to tilt inward. The decreased tension on the spring lowers the valve and allows oil to drain from the propeller hub. As this happens, aerodynamic forces acting on the propeller blades decrease the blade angle, resulting in an increase in RPM. With this type of system, a loss of oil pressure or governor failure results in the propeller blades returning to low pitch. Most multi-engine aircraft have what is known as featherable constant-speed propellers, which allow the pilot to rotate the propeller blades so they are nearly aligned with the relative wind. This reduces drag should an engine fail. In this system, oil pressure is used in conjunction with aerodynamic forces to decrease the pitch of the propeller blades and a set of counterweights to increase the pitch. When the propeller is spinning, centrifugal force pulls the counterweights toward the propeller's plane of rotation. When oil pressure is removed, the counterweights overcome the aerodynamic forces on the propeller and rotate the blades to their feathered position. Now let's take a look at some operational considerations when using a constant speed propeller. Although engine designs vary, as a rule, you should avoid excessively high manifold pressures with low RPM settings, because high cylinder pressures can damage the engine. One way to avoid this is to always keep the prop control in the high RPM or full forward position during ground operations, takeoffs, and landings. Another way to keep from damaging the engine is to follow some basic procedures when decreasing and increasing engine power. For example, when reducing power, first decrease the manifold pressure with the throttle. Then decrease the RPMs with the propeller pitch control. It's important to note that as propeller RPM decreases, manifold pressure increases slightly. Therefore, to avoid excessive manifold pressure for a given RPM, it's best to initially reduce the manifold pressure below what is desired. Then, after the RPM is set, adjust the throttle to the desired setting. When increasing power on an aircraft with a constant speed propeller, begin by increasing the RPM, then advance the throttle. Constant speed propellers can give you better climb rates, higher cruising speeds, and extended endurance due to reduced fuel consumption. However, since the combination of manifold pressure and RPM setting needed to achieve a specific performance varies from one aircraft to another, always consult the pilot's operating handbook for the recommended power settings. So far, we have looked at how fuel injection, turbocharging, and constant speed propellers can increase engine performance. But as you extract more from the engine, it becomes more and more important that we observe the operating limitations and follow the procedures established for the aircraft by the manufacturer.
Environmental and ice control systems have been developed to allow pilots to comfortably fly at relatively high altitudes and in a variety of weather conditions. Ventilation, air conditioning, and heating systems compensate for hot and cold temperatures, while oxygen and pressurization systems overcome our physiological limitations. In addition, to take advantage of the increased aircraft capabilities, ice control systems were developed to allow pilots to fly into known icing conditions. The following discussion covers some common environmental and ice control systems. But before you use any of the systems in your aircraft, you should consult your pilot's operating handbook. Let's begin with air conditioning systems. The most common type of air conditioner found on general aviation aircraft is a vapor cycle system. These systems are very similar in operation to the systems found in an automobile or refrigerator. To activate the system, controls are provided in the cockpit. Normally, these controls include an on-off switch, a thermostat control, and a fan control. When the system is turned on, a pump compresses Freon vapor and sends it to a condenser, which is exposed to the free airstream. Here, the Freon cools and turns into a liquid. Then the Freon goes to a receiver dryer, which acts as a reservoir to ensure there is enough coolant available to meet system demand. In the receiver dryer, the Freon goes through a filter dryer. The filter removes contaminants, while the dryer contains a material that attracts and removes moisture, which could freeze in the refrigeration system and plug the line. The Freon then goes to an expansion valve where the pressure is reduced. This further cools the liquid. From there, the Freon goes to the evaporator, or heat exchanger. Here, the liquid Freon changes to a vapor. Cabin air is then passed through the evaporator. Since the cabin air temperature is warmer than the temperature of the vaporized Freon, the Freon absorbs heat from the cabin and makes it more comfortable to you and your passengers. Finally, the vapor is returned to the compressor and the cycle starts over. For winter flights or flights in colder temperatures, a cabin heater is often more essential than an air conditioner. There are two basic types of heaters: the heat exchanger and the combustion type. The first one we'll discuss is the heat exchanger, which is commonly found on single-engine airplanes. These systems pass cool ambient air through a shroud surrounding a hot component in the engine compartment, usually the exhaust system. This heats the air, which is then vented to the cabin. One danger associated with this type of system is the possibility of carbon monoxide leaking into the heating system through a defect in the exhaust system. Carbon monoxide can quickly and severely reduce your flying ability and can even cause death. If you suspect a leak or smell exhaust fumes in the cockpit, turn off the heater, open the fresh air vents or windows, and use supplemental oxygen if it's available. The other heating system is the combustion type, which is like the gas furnace in most homes. This type of heater is commonly found on multi-engine airplanes because the location of the engines make heat exchangers inefficient and impractical. This system uses a blower to force hot air from the combustion heater to the cabin. Although combustion heaters operate independent of the engines, they rely on the same fuel supply. Therefore, you should plan on increased fuel burn and decreased range when using this type of heater. If the heater overheats, an over-temp switch shuts the heater off to prevent a possible fire. In most aircraft, this over-temp switch cannot be reset from the cabin. Therefore, you'll have to continue the flight without heat, or land and reset the system. However, before flying again, make sure you've determined and corrected the malfunction. Another environmental control system commonly found on high-performance aircraft is an oxygen system. Federal aviation regulations require the use of supplemental oxygen above certain altitudes in order to compensate for the body's inability to get enough oxygen through normal respiration. There are three types of oxygen systems: continuous flow, diluter demand, and pressure demand. The first one we'll look at is the continuous flow system. This system is commonly found on general aviation aircraft and can be portable or permanently installed. Whether permanent or portable, the continuous flow system has four basic components: a high-pressure supply cylinder, a pressure regulator, a distribution system, and a continuous flow mask assembly. The oxygen supply is stored in one or more high-pressure cylinders. These cylinders must comply with strict quality standards and labeling practices. These labels identify the cylinder as containing aviators breathing oxygen, the date of the last hydrostatic test, and the highest pressure the tank can be charged to. Normally, this is 1,800 pounds. A gauge displays the pressure in the cylinder, while the on-off valve is used to start oxygen flow. On portable units, the gauge and valve are on the tank, while permanent installations often have these controls in the cabin. A pressure regulator reduces cylinder pressure to a usable level. This regulator may be manually operated or automatic. A manual regulator works the same as a water faucet. Opening the valve increases flow. The disadvantage of a manual regulator is that you must readjust it as you're changing altitude. With an automatic regulator, all you have to do is activate the system with the on-off valve. The system then compares the atmospheric pressure and cylinder pressure and adjusts the flow accordingly. In aircraft with permanent installations, oxygen outlets are located in various places throughout the cabin. Each outlet has a spring-loaded check valve to prevent oxygen leaks and allow oxygen to flow only when a mask is plugged into the outlet. The mask assembly for a continuous flow system consists of the plug-in connector with the flow restrictor, a supply hose with a flow indicator, a rebreather bag, and the mask itself. The plug-in connector has different size openings depending upon who will be using the mask. A larger opening connector is used by pilots and crew since they require more oxygen than the passengers. These connectors are usually color-coded with the passenger's supply hose marked with a gold or orange band. The pilot supply hose is marked in red. The flow indicator shows that oxygen is flowing to the mask. This device is simply a spring-loaded check valve. When the oxygen is flowing, the pressure overcomes the spring and deflects the colored valve toward the mask. The rebreather bag helps conserve the oxygen supply by mixing the oxygen with outside air. Oxygen flows continuously into the bag, causing it to expand. As you inhale, the bag collapses and outside air is drawn in through small holes in the mask. The bag is partially refilled by unused air exhaled by the user and partially by oxygen from the storage cylinder. Unused air is forced out the holes in the mask. As altitude increases, the greater flow of oxygen causes the bag and mask to be pressurized more. This results in less outside air entering the mask. In addition, the higher altitude causes the bag to expand due to the lower surrounding pressure. The continuous flow system is adequate up to 25,000 feet. Above 17,000 feet, however, you must be careful to maintain a tight seal between the mask and your face. Above 25,000 feet, you and your passengers should use some form of demand oxygen system. The diluter demand is one of these systems and is the next one we'll discuss. A diluter demand system shares the same components as a continuous flow system, except there is no rebreather bag. Instead, an additional regulator is incorporated in the mask or hose assembly. As the name implies, the diluter demand system supplies oxygen only when you inhale, and virtually all the exhaled air is forced out of the mask. As altitude increases, the regulator increases oxygen flow. Normally, you'll receive 100% oxygen by 30,000 feet, but you can select 100% oxygen at any time. The third type of oxygen system is a pressure demand system. These are more commonly installed in turboprop and jet aircraft because of their high cruise altitudes. These systems are primarily used in case the cabin pressurization system fails. At high altitudes, there is not enough atmospheric pressure to allow you to breathe normally, so oxygen is forced into your lungs. The use of pressure demand oxygen requires additional training since special techniques are required for its use. Regardless of the type of oxygen system installed in your aircraft, it's very important to have a sufficient supply of oxygen available for the planned flight. To make sure you have enough oxygen, you should use an oxygen duration graph or chart. To use this particular type of graph, you have to know how much oxygen is available and how many people will be using the system. The oxygen available is indicated in pounds per square inch of pressure on a gauge. In this example, you have 1,800 pounds in the cylinder. To find out how much oxygen is available for the pilot and 2 passengers, locate 1,800 psi on the chart, then move to the line representing the consumption rate for the pilot and 2 passengers. Next, locate the duration of oxygen available. In this case, it is slightly more than 2 hours. The pre-flight inspection should also include a check of the system itself. This can be done by turning the oxygen system on and checking each outlet for flow. Finally, brief your passengers on the use of oxygen and stress the importance of not smoking, since smoking poses a serious fire hazard. If the oxygen system fails during a flight, or if oxygen is not used for high-altitude flights, you may suffer from hypoxia. Hypoxia is caused by a lack of oxygen. Symptoms for hypoxia vary from one person to the next, but one of the first things to be affected is your judgment. Here is a list of the common symptoms. Since hypoxia impairs judgment and may not be easily recognized, it is very important to take corrective action before hypoxia develops. The FAA recommends that oxygen be used above 10,000 feet during the day and as low as 5,000 feet at night. A condition with similar symptoms to hypoxia, but from an entirely different cause, is hyperventilation. Hyperventilation is a deficiency of carbon dioxide, which causes a chemical imbalance in the bloodstream. Hyperventilation results from deep, rapid breathing, which is normally an involuntary reaction to stress, tension, anxiety, or fear. Since the symptoms of hyperventilation are similar to hypoxia, it is often best to treat the victim for both. With hypoxia, 3 or 4 deep breaths of pure oxygen should relieve the symptoms. If this doesn't work, have the individual breathe into a sac and make a deliberate effort to relax and slow the breathing rate. Talking aloud may also help. Since oxygen use may make some passengers nervous, pressurized airplanes are often more desirable. Other advantages include freedom to move around the cabin and talk more easily, as well as an increased comfort level because of small changes in atmospheric pressure. An aircraft pressurization system receives compressed air from a turbocharger or the compressor section of a turbojet engine. The advantage of obtaining air from these sources is the fact that the compressor system is already there. The disadvantage is that this air is very hot. Therefore, the compressed air is passed through a heat exchanger to cool it down. Since the cabin must contain the compressed air, it is designed and built at the factory to maintain a predetermined pressure differential based on performance goals. In this example, the airplane's cruise performance is best at 24,000 feet, where the pressure is 5.8 psi. However, the desired cabin altitude is 8,000 feet, where the pressure is 10.5 psi. This means the cabin must maintain a pressure differential of 4.7 psi. The pressure differential is maintained by an outflow valve. This outflow valve automatically opens and closes to maintain a selected cabin pressure. Failure of the outflow valve may cause excessive pressure to build, so a safety release valve is installed in the cabin. If cabin pressure approaches the design limits of the airplane, this valve opens to relieve the pressure. This valve can also be connected to the landing gear safety switch so that any time the gear is down and the switch is open, the cabin depressurizes. It may also be manually opened in case a turbocharger fails and contaminated air enters the cabin. There are 2 types of pressurization systems: a basic system and a controllable system. All you have to do with a basic system is turn it on. When the airplane reaches a preset altitude, commonly 8,000 feet, it will begin to pressurize. As the airplane continues to climb, the cabin altitude will remain at 8,000 feet until a second preset altitude is reached. Past this point, which is commonly 20,000 feet, the cabin altitude increases as the airplane climbs. A controllable system is more complex, but it allows flexibility and control that the basic system lacks. With a controllable system, the pilot can choose where pressurization begins. For instance, you can begin pressurizing the cabin at pattern altitude, and the cabin remains at that altitude until it reaches the maximum allowable pressure differential. Then, the outflow valve maintains this pressure differential as the aircraft climbs. The outflow valve in a controllable pressurization system can also be controlled to adjust the rate at which the cabin is pressurized or depressurized. This means the airplane can descend at 2,000 feet per minute to comply with ATC instructions. But to keep the passengers comfortable, the cabin pressure can be adjusted to descend at 500 feet per minute. To increase the utility of an aircraft, it may be necessary to operate in conditions where icing is possible. While your primary goal is to avoid icing conditions, anti-ice and de-ice systems allow you to control or prevent icing to a certain degree. To legally fly in known icing conditions, an aircraft has to be certified by the FAA for that type of operation. This certification includes installation of anti-icing and de-icing systems designed to keep the airframe, propellers, and windscreen free of ice. Let's take a closer look at some of these systems. Anti-ice systems prevent ice formation, whereas de-ice systems are used to free the aircraft of ice that has already accumulated. Probably the most common anti-icing device is the pitot heater. A heater coil of high-resistance metal is built into the pitot tube housing. When the switch in the cockpit is activated, the coil's high resistance causes it to heat up and prevent the formation of ice. Many piston-powered aircraft have pneumatic airframe de-icing systems on the leading edges of wings and tail surfaces. Normally, this system consists of inflatable boots, engine-driven pressure and vacuum pumps, a timer, and pneumatic regulators. The engine-driven pressure pump inflates the boots while the vacuum pump deflates the boots and supplies enough suction to keep the boots flat against the leading edge of the wing. The timer controls the inflation-deflation cycle. The regulator ensures the boots don't overinflate. It also may alternate the inflation and deflation of various sections of each boot to minimize the disruption of the airflow caused by the inflation of the boots. While you should follow the manufacturer's recommendations as to when to operate the system, the general procedure is to allow 1/4 to 1/2 inch of ice to accumulate before activating a pneumatic system. If the ice is too thin to break away cleanly, it may refreeze, leaving a space between the ice and the wing. Further attempts to de-ice the wing may be ineffective because the boots inflate within the cavity and don't break the ice. The second type of airframe ice control is the anti-icing system found on turboprop and jet aircraft. This system uses heated engine air routed to the leading edges of the airfoils to keep them above freezing. Heat is also used to control ice on propellers and windscreens, but heated engine air is impractical, so electrical energy is used instead. Oil and wear-resistant pads embedded with electrical heating elements are bonded to propellers. Electricity is supplied to these pads through wire brushes in the propeller hub. Since centrifugal force is sufficient to throw ice off the outboard section of the propeller, the pads usually heat only the inboard section. Some propellers are protected against the formation of ice by coating the blade surface with alcohol, usually isopropyl alcohol. With this system, alcohol is sent to a slinger ring. Injector tubes on each blade pick up the alcohol from the slinger ring and direct it to the propeller blade. Windshields may be protected with alcohol, but normally they are electrically heated. Tiny electric heating elements are laid in the windscreen or windshield panel to heat it up and melt any ice. Before flight, anti-icing chemicals may be applied to the airframe, propellers, and windshield to lessen the chance of ice adhering to these parts. Used together with anti-icing and de-icing systems, these chemicals can be very effective. Of course, flight in icing conditions may be hazardous regardless of how your aircraft is equipped. Before you enter areas of known icing, you should be sure that all of your systems are operating correctly and that you're familiar with the specific equipment installed on your aircraft. It's also a good idea to limit your exposure to icing conditions. Some of the systems described may handle ice better than others. The aircraft systems we have discussed in this section are designed to increase comfort and to allow you to adapt to an environment of reduced atmospheric pressure and oxygen levels, as well as the danger of structural icing. Thorough knowledge of the systems installed in your aircraft and good operational practices will lead to many enjoyable hours of flying.
Another system commonly found on high-performance aircraft is retractable landing gear. Retracting the gear streamlines the airplane and reduces parasite drag. This leaves more power available for better climb performance and higher cruise speeds. There are many different types of retractable landing gear, from the types found on large commercial transports to those on high-performance single-engine aircraft, with each one being identified by the power source used to extend and retract the gear. In this section, we'll look at the most common types of retractable landing gear systems: the electrical and the hydraulic. In both the electrical and hydraulic systems, you control the position of the gear by a landing gear lever located in the cockpit. By moving this lever, a signal is sent to the power source, which in turn supplies the necessary energy to raise or lower the gear. One thing you always want to do is verify you're moving the correct lever. Even though the gear and flap levers are shaped differently, a few pilots have thought they were raising the flaps, but inadvertently raised the gear. To prevent this from happening, most manufacturers have included a safety detent in the lever assembly. In order to raise or lower the gear, you must lift the lever over this detent. When transitioning to a different aircraft, make sure you're familiar with the layout of the controls. Some aircraft have the location of the gear and flap handles reversed. The first type of system we'll examine in detail is the electrical gear system. In this particular aircraft, each landing gear is mechanically linked to a gearbox, which is located in the fuselage just behind the pilot's seat. By moving the gear handle, power is supplied to an electric motor, which drives the gear toward the selected position. The motor will keep running until the up or down limit switch on the gearbox disconnects the electrical power to the landing gear motor. Should the gear fail to extend due to loss of electrical power, it can be extended by using a manual hand crank located on the floor in front of the pilot's seat. When the emergency handle is placed in the operating position, it automatically disengages the landing gear motor from the actuator box, allowing you to hand crank the gear into the down and locked position. However, because of limitations on most systems, the hand crank cannot be used to retract the gear once it is down and locked. The next system we'll look at is the hydraulic landing gear system, which uses an engine-driven pump. In most cases, the pump is located on the accessory section of the engine and uses a series of valves, pipes, and hydraulic actuating cylinders to transfer the hydraulic fluid necessary to raise and lower the gear. This system also has an emergency feature should an engine or hydraulic pump fail. Backup hydraulic pressure can be supplied by an electrically driven hydraulic pump, or in the case of some small general aviation aircraft, by a hand pump. In the unlikely event of a hydraulic leak or loss of hydraulic fluid, some aircraft have tanks of compressed air that may be used to blow the gear into the down and locked position. Another type of retractable gear is the hydraulic system, which uses an electrically driven hydraulic pump. This system is referred to as an electro-hydraulic system. Pressure in one direction raises the gear and holds it in the up position, while pressure in the opposite direction lowers the landing gear. Most hydraulic systems have an internal pressure switch, which automatically operates the hydraulic pump when system pressure falls below a specified range. This pressure is supplied to hydraulic actuator cylinders, which are attached to the gear assembly. These cylinders do the actual raising and lowering of the gear. In some systems, the gear is held up with hydraulic pressure. However, some manufacturers also use hydraulically actuated uplocks to hold the main gear in the up and locked position. In addition to hydraulic pressure, Some aircraft have a heavy-duty spring attached to the gear assembly to help extend the landing gear into the down and locked position. To prevent inadvertent retraction of the gear during ground operations, most systems incorporate a mechanical squat switch located on the landing gear strut. When this switch is compressed by the weight of the aircraft, it does not allow the gear to retract. However, if the gear handle is in the up position and pressure is removed from the switch, the gear attempts to retract. This could be especially hazardous on takeoff. During normal operations, the gear should be retracted only when a positive rate of climb has been established and you can no longer land on the remaining runway. The emergency extension for an electrohydraulic system may consist of a pressure dump valve which relieves system pressure and allows the gear to free fall into the down and locked position. On most aircraft, a hand pump is required to supply system pressure for lowering the gear. To determine the status of the gear, indicator lights are installed. There can be one or more lights located near the gear handle. When the gear is down and locked, a green light appears. Gear in transit or in any other position besides down and locked may be indicated by an amber or red light. In most aircraft, these lights can be dimmed. This prevents them from becoming a distraction during night flights. In this example, rotating the light itself reduces the brightness. Some landing gear indicator lights have a push-to-test feature, so you can quickly determine if the bulb is burnt out. Another way to determine if a bulb is burnt out on systems with more than one light is to switch the bulb with one that is already illuminated. Most systems are set up so that all of the gear lights are interchangeable. In this way, you can quickly determine if the problem is in the lights or the gear itself. Some aircraft also incorporate a small mirror to help you visually determine if the gear is down. Another feature found on most retractable gear aircraft is a landing gear warning system. This usually consists of a warning horn that sounds when the gear is not down and locked, and the throttle is reduced below a specific point. A similar system also alerts the pilot that the gear is not down and locked when the flaps are lowered beyond a specific flap setting. The gear on some systems automatically extend when the airspeed drops below a designated value. This system also prevents the gear from retracting when below this airspeed. These auto-extension type safety features may be disarmed so the aircraft can be maneuvered with the gear up at slower speeds. For example, this system must be overridden in order to retract the gear during a maximum performance takeoff. Due to the forces imposed on the landing gear by gravity and the airstream, manufacturers have designated a couple of airspeed limitations for landing gear operations. The first is maximum landing gear operating speed, or VLO, which is the maximum speed that the gear may be safely extended or retracted. The other is maximum landing gear extended speed, VLE. This is the maximum speed you can fly with the landing gear in the down and locked position. These airspeed limitations are not shown on the airspeed indicator. However, they are listed in the pilot's operating handbook as well as placarded on the panel. Exceeding these airspeed limitations can cause structural damage to the aircraft and to critical landing gear components. During cold weather operations, slush and ice can build up on the landing gear assembly. To help prevent this from happening, try to avoid taxiing through standing water prior to takeoff. After takeoff, if there is a chance that moisture is on the gear, leave it extended slightly longer than normal to allow the air to blow it off. In this volume, we have taken a look at some of the components of high-performance aircraft, including fuel injection and how it improves the power output of your engine through better fuel distribution. Next, we looked at how constant speed propellers allow you to alter propeller blade angle to obtain optimum performance throughout a variety of airspeeds, and how turbochargers help your engine develop maximum power at altitudes well above sea level. We also learned how environmental systems can help you and your passengers remain comfortable during high-altitude flights, and how ice control can provide an additional safety margin during IFR operations. And finally, we saw how the components of different retractable landing gear systems work together to raise and lower the landing gear. Remember, each make and model of aircraft has its own distinct operating characteristics and design features. These advanced aircraft systems require you to study the pilot's operating handbook in order to thoroughly understand the different systems and take full advantage of their benefits.
In this program, we'll discuss short field operations, which are listed as maximum performance takeoffs and landings in the Commercial Pilot Practical Test Standards. We'll also look at how to perform soft field takeoffs and landings. While these maneuvers are practiced separately, there are times when you might need to combine the techniques. The first maneuver we'll discuss is the short field takeoff and climb. For training purposes, if an actual obstacle doesn't exist, you should assume there is a 50-foot obstacle at the end of the runway. Make sure your airplane has the performance to take off under the existing conditions by checking the takeoff performance charts in the airplane's POH. During your pre-takeoff check, set the flaps as recommended in the pilot's operating handbook. Before you attempt a short field takeoff, position the airplane as close to the approach end as possible and align it with the center line. Hold the brakes and apply full power before releasing them. This procedure allows you to check engine performance before starting the takeoff roll. Maintain positive directional control by using nose wheel steering until the rudder becomes effective. Allow the airplane to accelerate with the stabilator in a neutral position for minimum drag. When you reach the recommended liftoff speed, smoothly and positively rotate the airplane to an attitude which will achieve the best angle of climb airspeed, or the recommended climb speed. Maintain this speed until the obstacle is cleared. Attitude control is very important during the rotation to minimize the ground roll and maximize climb performance. If your pitch attitude is too high, induced drag becomes excessive. This significantly decreases acceleration and extends the ground roll. On the other hand, an attitude that is too low delays liftoff, which again increases the ground roll. When you're clear of the obstacle, accelerate to the best rate of climb speed and slowly retract the flaps. If you're flying an airplane equipped with retractable gear, you should raise it as soon as you have established a positive rate of climb and can no longer land on the remaining runway. Landing on a short runway, or on one which has the landing area restricted because of obstacles, requires a short field landing technique. Preparation for the landing begins on the downwind leg. There you should slow to pattern speed and extend the flaps to the first position. If your airplane is equipped with retractable gear, lower the landing gear. It's recommended that you extend the second increment of flaps while on the base leg, and full flaps when on final. All the while, progressively reduce airspeed to smoothly transition to the short field approach speed. Ideally, the final approach is conducted at a constant glide angle, airspeed, and power setting. The objective of the short field landing is to clear the obstacle, land safely, and stop the airplane with little or no floating. This requires precise control of airspeed and descent angle. Establish the approach speed early on the final approach. Normally, the recommended speed is not more than 1.3 times the power-off stalling speed. However, in gusty wind conditions, you might want to increase your airspeed to help maintain control of the airplane. Once your pitch attitude is established for the correct angle of descent, you may need only small power changes to control your airspeed. If you maintain the recommended airspeed, you'll touch down near the designated point on the runway with very little floating. After touchdown, lower the nose as soon as practical and apply maximum braking procedures. This usually includes holding back pressure on the control wheel to transfer more of the aircraft's weight to the main gear. Maintain positive directional control and follow the recommendation in the POH for flap retraction. If you touch down at the correct speed and smoothly apply maximum braking, the landing roll will be extremely short. Soft field techniques must be used when the runway surface is covered with snow, sand, tall grass, or mud. You may also want to use these same procedures to minimize the problems associated with a rough surface. If the taxiway is also soft or rough, the soft field procedure actually begins in the parking area. Plan ahead so you can keep the airplane rolling once you start taxiing. This might mean you will have to complete the pre-takeoff checks in the parking area. Once you begin to taxi, keep the airplane moving at a steady speed. You can relieve some of the weight on the nose gear by holding the control wheel in the full aft position. Before you taxi onto the runway, however, make sure the traffic pattern is clear and that all pre-takeoff checks are complete. If the approach and departure paths are clear, taxi onto the runway. When you're aligned with the middle of the runway, smoothly apply full throttle. As the engine reaches full power, check your engine instruments to verify proper operation. Continue to hold back pressure on the control wheel and maintain positive directional control. The rudder will become more effective as your speed increases. The objective of the soft field takeoff is to minimize the friction between the landing gear and the runway. To do this, you need to establish and maintain a nose-high pitch attitude as soon as possible during the takeoff roll. However, with increased speed, you have to release some of the back pressure to maintain the pitch. With the proper technique, the airplane will fly itself off the runway at an airspeed lower than the normal liftoff speed. This occurs because of ground effect. Once airborne, lower the nose slightly and accelerate in ground effect, but make sure you keep the landing gear clear of the surface. If there are obstacles in your flight path, accelerate to VX or the climb speed recommended in the POH. If obstacles aren't present, accelerate to VY. Once you've achieved a positive rate of climb and can no longer land on the remaining runway, retract the gear if appropriate. When you are clear of all obstacles, raise the flaps according to the recommendations in the POH and complete the after takeoff checklist. Now let's take a look at a soft field landing. Your objective here is to delay the transfer of weight from the wings to the landing gear until the airplane is at the slowest possible speed. The pattern and approach are normal, except you use enough power during the flare to help arrest the rate of descent. There is no need for a steep glide angle unless there are obstacles in the approach path. After you're established on final, maintain precise control of your airspeed, rate of descent, and ground track. Prior to touchdown, establish a nose-high landing attitude which allows the main gear to contact the surface with the nose wheel clear of the ground. Using power during the flare creates more airflow over the tail surfaces and helps you control the descent. The touchdown should occur just above the stalling speed. Deceleration is usually rapid on a soft surface, so the use of brakes may not be needed. In fact, the use of brakes could cause the nose wheel to dig into the surface and the aircraft to nose over. Retract the flaps as recommended. It is usually preferable to leave the flaps down during the landing roll so your attention focuses on maintaining positive directional control. You will probably need to add more power than usual as you're taxiing to the parking area. You should also maintain back pressure on the control wheel. When clear of the runway, complete the after-landing checklist. Proficiency in maximum performance takeoffs and landings allows you to safely take advantage of small and soft runways. This enables you to increase your airplane's usefulness and lets you get to areas not served by airports with long, hard-surfaced runways.
As you progress in your training, you will develop the ability to precisely control your aircraft by learning how to execute a number of maximum performance maneuvers. The steep turn develops your ability to accurately control the airplane in a maximum performance turn. You'll perform the maneuver at a constant altitude using a bank of 50 degrees. This maneuver can be performed to the left or right. As you should do when performing all training maneuvers, start by making clearing turns to ensure that the area is free of conflicting traffic. Then continue to look for traffic throughout the maneuver. Take a moment to stabilize the airplane at a constant altitude, heading, and airspeed. Begin the maneuver only after you're comfortable with the airplane's configuration. The altitude you select should allow you to complete the maneuver no lower than 1,500 feet AGL. Although any initial heading will do, you might find it helpful to start on one that is aligned with a road, section line, or other prominent landmark. The airspeed you select should not exceed the airplane's design maneuvering speed. This is very important because a steep turn substantially increases load factor. In a 50-degree constant altitude bank, the airplane is exposed to about 1.6 Gs. It's also important to monitor your airspeed throughout the maneuver, and remember that stall speed increases as bank angle increases. For example, if the stall speed is 50 knots with 0 degrees of bank, it increases to 63 knots at 50 degrees of bank. To maintain altitude with this increased load factor, you must increase lift. If you fail to do this, you will enter a spiraling descent. To prevent this, smoothly apply power and stabilator back pressure as the bank steepens, while maintaining coordinated flight with aileron and rudder. During this maneuver, you will most likely experience an overbanking tendency. This occurs because the wing on the outside of the turn is developing more lift than the wing on the inside of the turn, causing the airplane to roll beyond your desired bank. You might have to counter this overbanking tendency by applying a slight amount of aileron in the direction opposite the turn. When you reach your desired bank, confirm the accuracy of the maneuver by cross-checking the attitude indicator for proper bank, the altimeter and VSI for proper pitch, and the turn coordinator for coordinated flight. As you maintain the turn with outside visual references, you may wish to trim the airplane to eliminate the excessive control wheel pressure required to maintain altitude. If so, you must anticipate the forward pressure that will be needed during the recovery from the turn. One way to help maintain the proper pitch attitude is to select a spot on the windshield that is on a direct line between your eyes and the horizon. With a constant bank angle, you can determine proper pitch attitude by keeping the spot aligned with the horizon. Be alert for anything that might affect your altitude. For instance, if you allow the bank angle to decrease, the back pressure on the control wheel will be too great. The nose will rise and you'll start to climb. Generally, a small increase in bank angle allows you to return to your altitude. Another situation occurs when you begin losing altitude. If you attempt to climb back to your altitude by pulling back on the control wheel, you only tighten the turn and increase the load factor. The result is a tight descending spiral, an accelerated stall, or possibly structural damage. To properly regain altitude lost during a steep turn, begin by decreasing the bank angle to reduce the load factor and allow the pitch attitude to increase. Once you've returned to your desired altitude, re-establish the bank angle and apply the proper back pressure to re-enter the maneuver. The recovery from the turn should be as smooth and precise as the rest of the maneuver. Anticipate the rollout by applying the general rule of thumb of 1/2 your bank angle. In this situation, the rollout should begin approximately 25 degrees before the recovery heading. As you roll out of the turn, the load factor imposed on the airplane is reduced quickly. This means you must decrease both back pressure and power to maintain altitude. If you use stabilator trim at the start of the turn to relieve control pressure, be prepared to exert forward pressure on the control wheel as you recover to prevent the airplane from climbing. Then retrim as necessary. While practicing the maneuver, a steep turn in one direction might be followed by one in the opposite direction. As you begin your rollout on the predetermined heading, gradually reduce back pressure until the airplane is wings level. Then begin to increase back pressure as you immediately roll into a 50-degree bank in the opposite direction. Because the nose appears lower in a right turn, you may have a tendency to gain altitude. Therefore, once you've determined that you're maintaining altitude by cross-checking the VSI and altimeter, select a new spot on the windshield to help you maintain the correct pitch attitude. Practicing steep turns will increase your confidence and ability to control the airplane smoothly. Proficiency in these maximum performance maneuvers will also improve your everyday flying skills. Another maneuver that requires a high level of planning, coordination, accuracy, and smoothness is a chandelle. The precise execution of a chandelle reveals that you have developed a thorough knowledge of how pitch, bank, airspeed, and control input must be coordinated to achieve the airplane's maximum performance capabilities. A chandelle is described as a maximum performance climbing turn with a heading change of 180 degrees. Perform the procedure with full power and smoothly increase the pitch attitude so the airspeed gradually decreases to just a few knots above the airplane's stall speed as you roll out on the recovery heading. Although obtaining maximum climb performance is an objective of a chandelle, gaining altitude is not as important as proper timing and coordination. As with steep turns, you should perform chandelles at least 1,500 feet AGL and make the necessary clearing turns prior to starting the maneuver. It's recommended that you establish yourself on a crosswind heading that will enable you to perform the chandelles into the wind. This minimizes the effect of wind drift and helps you remain in the practice area. You should also select a heading that is aligned with a prominent feature, such as a road or section line, to help you monitor your progress during the maneuver. Part of your preparation includes configuring the airplane at its maneuvering speed or the recommended entry speed. By remaining at or below this speed, you should not exceed the limit load factor. Once this is established, begin the maneuver by smoothly rolling into a 30-degree coordinated bank. Then apply control wheel back pressure to increase your pitch attitude and add full power. During the first 90 degrees of turn, you're concentrating on maintaining the initial 30 degrees of bank while gradually increasing pitch, so that maximum pitch attitude is attained precisely at the 90-degree point. As you pass through the 90-degree point, concentrate on maintaining the nose-high attitude and slowly begin to roll out of the bank so that you reach a wings-level attitude at the 180-degree point. When you roll out on the recovery heading, the airspeed should indicate just above stall speed. With practice, you'll learn to coordinate your rollout at a precise airspeed. Since full power is used throughout the maneuver, your airspeed is controlled by adjusting your pitch, which is the key to properly executing the chandelle. You'll find that if you increase your pitch attitude too rapidly in the turn, the airplane may stall before you complete the 180-degree turn. On the other hand, if you increase pitch too slowly, you'll have excessive airspeed at the completion of the maneuver. At the rollout point, the controls will feel mushy due to the low airflow over them, and more deflection will be needed to control the airplane. You'll also experience the left-turning tendencies produced by P-factor and spiraling slipstream. As with any phase of flight, control the adverse yaw by referring to the turn coordinator and keeping the ball centered. Hold the rollout heading momentarily, and then smoothly recover by slowly lowering the nose to a level flight attitude. Your objective is to allow the airplane to accelerate back to cruise airspeed while maintaining a constant altitude. Practicing chandelles will help you learn positive control techniques at varying airspeeds and attitudes, which will improve your ability to control your airplane during maximum performance maneuvers. As you continue practicing commercial maneuvers, you'll be introduced to advanced figure 8 procedures. Let's take a look at a maximum performance maneuver called a lazy 8. Because the procedure incorporates various combinations of climbs, descents, and turns, you must have a complete understanding of the airplane's performance capabilities. In addition, the maneuver will help you develop and improve your coordination, division of attention, and ability to precisely control the airplane. Basically, you'll perform 2 180-degree turns in opposite directions. Each turn contains a climb and a descent to return to your entry altitude and airspeed. The Lazy 8 should be flown just as its name implies, in a smooth, gentle manner. Before beginning, establish yourself at an altitude that allows you to complete the entire maneuver at least 1,500 feet above the ground, and determine the wind direction so you can start the Lazy 8 on a crosswind heading. Plan to make the turns into the wind so you won't drift from the practice area. This will also help you maintain symmetrical loops. As you do when practicing all maneuvers, clear the area before you begin. Then remain vigilant for traffic throughout the maneuver. Begin the maneuver by aligning the airplane on the entry heading. Then, to help maintain orientation, select a 90-degree reference point. This point should be on the horizon and abeam your flight path. Additional reference points at 45 degrees, 135 degrees, and 180 degrees are also helpful. Start in straight and level flight at a normal cruise power setting and at the recommended airspeed. Since the power setting does not change during this maneuver, pitch attitude controls airspeed. When abeam the 90-degree reference point, begin the maneuver. During the first 45 degrees, concentrate on performing a gradual climbing turn toward your reference point. At the 45-degree point, you should reach your greatest nose-high pitch attitude. The bank angle should be approximately 15 degrees and increasing. Since your airspeed decreases during the climb, maintain coordinated flight by using enough right rudder to counteract torque. Throughout the second 45 degrees of turn, continue to increase your bank and smoothly lower the nose. Your objective is to pass through the 90-degree point in a level pitch attitude and at the maximum bank angle, which is approximately 30 degrees. At this point, you should also be at the maximum altitude and minimum airspeed. This speed for most general aviation training aircraft is slightly above the stall speed. As you pass through the 90-degree point, gradually lower the airplane's nose and slowly decrease the bank angle. Your goal is to reach the 135-degree point at the greatest nose-low pitch attitude. The bank angle should be approximately 15 degrees and decreasing. As the airspeed continues to increase, maintain coordinated flight and time your rate of rollout and pitch change so you reach straight and level flight at the 180-degree point. This should be abeam the 90-degree reference point at your entry altitude and airspeed. Immediately enter a climbing turn in the opposite direction. Complete each 45-degree segment in the same manner as it was performed during the first half of the maneuver. As you practice lazy 8s, you'll develop the timing and coordination needed to achieve the proper pitch and bank adjustments. For instance, you'll find that if you apply insufficient nose-high pitch during the climbing turn, you might reach the 90-degree point with excessive airspeed. On the other hand, increasing pitch too rapidly could cause you to gain too much altitude, lose too much airspeed, and possibly stall the airplane. Another possibility is to improperly reduce bank during a descending portion of the maneuver. This will cause you to overshoot or undershoot your rollout heading. Just remember, the control pressures during a lazy 8 should be gradual and smooth, resulting in a slow, gentle, coordinated procedure. Another ground reference procedure that involves flying in a figure 8 pattern around 2 points on the ground is the 8s on pylons. During 8s on pylons, you don't maintain a uniform radius around the pylons, nor do you try to maintain a constant altitude. Instead, your goal is to vary your altitude and airspeed to keep a reference point, usually located near the wingtip, on the pylons. This reference point varies depending on your sitting height and position and the wing design of your airplane. Regardless of its exact position, the key to selecting the reference point is that your line of sight through the point must parallel the airplane's lateral axis. When performing 8s on pylons, you should maintain the reference point on the pylon so the airplane appears to pivot about it. The altitude that enables you to do this is called the pivotal altitude, and it is governed by your ground speed. As your ground speed increases, the pivotal altitude increases. Likewise, a decrease in ground speed causes your pivotal altitude to decrease. With all of this in mind, let's look at the planning and coordination needed to fly 8s on pylons. After clearing for traffic, start by determining the wind direction, and then select 2 pylons that are in an open area free of hills and obstructions. They should be spread far enough apart to permit a few seconds of straight and level flight as you fly between them. The pylons should be aligned perpendicular to the wind, and at approximately the same elevation to make altitude adjustments easier to accomplish. Plan to enter the maneuver near the pivotal altitude, which you can estimate by using this simple formula. First, approximate your true airspeed in miles per hour and square this value. Then, divide the product by 15. For example, if your true airspeed is 110 miles per hour, your approximate pivotal altitude is 807 feet AGL. You can also use the same formula with knots, but in this case, you will need to divide by 11.3. Since you seldom know your exact true airspeed, you'll need to find the desired altitude by experimenting as you fly the procedure. After you adjust power for the recommended entry speed, enter the maneuver by flying diagonally between the pylons. When you're approximately abeam the first pylon, roll into the turn. At this point, your ground speed is highest, which means you're at the highest pivotal altitude. As you continue the turn into the wind, your ground speed gradually decreases. If you fail to adjust for the reduced ground speed, the reference point moves behind the pylon. This means you're too high. To bring the reference point back to the pylon, lower the nose to descend to the pivotal altitude. As you proceed around the first pylon, your ground speed increases, so gradually raise the nose to keep the reference point aligned with the pylon. If you don't initiate the climb, the reference point moves ahead of the pylon. This means you're below the pivotal altitude. Remember, increased ground speed means an increase in the pivotal altitude. In addition, since a constant radius is not a requirement for this maneuver, you should not correct for any drifting. Therefore, use varying bank angle to keep the reference point on the pylon. The closer you are to the pylon, the steeper the bank. When the first turn is completed, roll out into straight and level flight for 3 to 5 seconds as you fly toward the second pylon. During this portion of the maneuver, you'll need to crab into the wind to correct for drift. Once you're abeam the next pylon, begin a turn in the opposite direction. As you continue the maneuver into the wind, ground speed decreases. Therefore, gently allow the airplane to descend to keep the wingtip reference aligned on the pylon. Correct for any deviations from your desired reference by gradually and smoothly adjusting your pitch attitude. During the final portion of the turn, your ground speed once again begins to increase. Thus, your pivotal altitude must subsequently increase to maintain the proper alignment. Continue the turn until you roll back to straight and level flight between the two pylons. The key to successfully flying 8s on pylons is to hold the reference point on the pylon by changing your altitude, rather than using uncoordinated rudder pressure. Coordinated flight should be maintained throughout the entire Figure 8 maneuvers. Commercial flight maneuvers are designed to help you attain a high level of competency in controlling the airplane. As you increase your ability to precisely execute them, you'll also increase your understanding of the airplane's maximum performance capabilities, as well as its limitations.
In this program, we'll look at the steep spiral, which is another maneuver that emphasizes planning, coordination, orientation, and aircraft control. Although the steep spiral is primarily a training exercise, it can be useful in some emergency situations. A steep spiral is basically a gliding descent using no more than 50 to 55 degrees of bank where you maintain a uniform radius around a reference point. The maneuver can be performed either to the left or right. Typically, you'll enter the procedure, complete 3 360-degree turns, then roll out on your entry heading. Let's look at how you perform the steep spiral. Your initial planning includes establishing the airplane at a height that will enable you to perform the procedure and recover at a safe altitude. After you've determined the location where you wish to perform the maneuver, clear the area by carefully looking for traffic below as well as in your general vicinity. To maintain orientation, you need to select a good ground reference point. The intersections of roads or fields are easily seen from the air. You should also select a prominent landmark near your entry heading. To aid you in rolling out of the maneuver, it's also a good idea to check your heading. Before starting the maneuver, stabilize the airplane at the recommended entry speed. This is the airspeed you should maintain throughout the procedure. Although any entry heading will do, you should try to enter the maneuver downwind. By doing this, you will use the steepest bank angle at the beginning of the maneuver. This then assures you that you'll be able to make the necessary adjustments in order to maintain a uniform radius. When you're ready to begin, apply carburetor heat if required and smoothly close the throttle. As you roll into the turn, you will probably have to lower the nose of the airplane to maintain airspeed. Use a reference spot on the windshield to maintain the correct attitude and periodically cross-check your airspeed. Remember, if the turn is to the right, you'll need to use a different reference point. When you first begin practicing steep spirals, you might find that using shallower bank angles and a larger radius of turn will help you become more comfortable with bank and airspeed control. Since one of the objectives of the maneuver is to maintain a constant radius about the selected reference point, you must adjust the bank to correct for any wind drift and changes in the ground speed. As you discovered while performing S-turns and turns about a point, ground speed and bank angle are directly related. The faster your ground speed, the steeper the bank needed to maintain a constant radius. Therefore, airspeed control is a critical factor in performing the maneuver. The faster your airspeed, the greater the ground speed and radius of turn. Since you're at idle power during this maneuver, you'll have to maintain airspeed by adjusting the pitch attitude. Periodically add power to clear the engine as you continue through the maneuver. This helps prevent excessive engine cooling and spark plug fouling caused by prolonged operation at idle power. To minimize ground speed variations, it's helpful to do this while heading into the wind. When you perform any maneuver in which high bank angles are used, it's important to maintain an awareness of the load factors imposed on the airplane. Any improper use of the controls can abruptly increase the load factor, which can lead to an accelerated stall or structural damage. In addition, pulling back on the control wheel to reduce excessive airspeed may actually tighten the spiral. The proper procedure to correct for excessive airspeed is to decrease bank angle, then apply back pressure. To recover from a steep spiral, use your heading indicator and the standard 1/2 of the bank angle, along with your chosen landmark to determine when to begin a smooth rollout. As you level the wings, smoothly adjust pitch to maintain your airspeed and continue a glide on the recovery heading. During practice, be careful not to descend below a safe altitude. One practical application of the steep spiral is during an emergency landing. If you lose power and have sufficient altitude, you can glide directly to your point of intended landing and then lose altitude by performing a steep spiral until you roll out on the downwind leg. As you're descending, you can inspect the site for obstructions or hazards. You can also determine the approximate wind direction and velocity. Adjust the spiral to roll out on a downwind heading as though you were going to make a normal approach at an airport. During an actual forced landing, you would continue to maintain your desired airspeed and plan on arriving at the key position with enough altitude so that you can land into the wind. The steep spiral is an excellent training maneuver because it helps you develop the ability to accurately control the airplane. In addition, it gives you a way to safely descend to the landing site should an actual emergency occur.
Let's look at another maneuver, the power-off 180-degree accuracy approach and landing. It's an approach to land with the engine at idle that uses only the glide angle under prevailing wind conditions to fly a specific pattern and land on the runway at a predetermined point. Power-off accuracy approaches and landings are designed to develop your ability to judge gliding distance and to control descent angle during a power-off approach to a safe landing. By understanding the power-off characteristics of your aircraft, you can improve your skills in estimating glide distance and in judging the effects of wind. The approach begins on the downwind leg with the aircraft at pattern altitude, typically no higher than 1,000 feet AGL. Make your normal pre-landing checks, including the extension of the landing gear if necessary. While on downwind, select your point of intended landing. Once you reach the downwind key position, which is opposite the point of landing, reduce the power to idle, adjust the pitch to maintain altitude, and decrease airspeed to the manufacturer's recommended power-off glide speed, or, if no speed is given, 1.4 VSO. Then lower the nose to maintain that airspeed. Your turn to the base leg of the pattern is governed by the existing wind conditions and glide angle. Stronger winds require a turn to base sooner than if lighter wind conditions prevail. Also, take into consideration the fact that strong headwinds affect your final approach as well. Use the turn to base leg to dissipate or conserve altitude as necessary to meet your intended landing position. Once you arrive at the base leg key position, which is 45 degrees from the intended landing position, lower your flaps as necessary and retrim the aircraft to maintain best glide speed. The turn to final is timed, so your rollout is aligned with the center line of the runway. Your goal on final approach is to descend at an angle that allows you to reach the intended landing position at an airspeed that results in little or no float just prior to touchdown. Remember, in a power-off situation, the pitch attitude controls the airspeed, which in turn controls the glide of the aircraft. Lower the flaps as necessary and make small adjustments to the pitch attitude to control your glide angle and airspeed. While your goal is to touch down within 200 feet of the point on the runway, but not before it, with little float, do not attempt to stretch the glide or retract the flaps in order to make the landing point. Concentrate on making a safe landing, then re-evaluate your downwind and base locations and flap positions for the next power-off approach attempt. Take time to evaluate your aircraft's performance in various wind conditions and with a variety of flap settings. Doing so enhances your ability to judge altitude, glide angle, and distance. If you can accurately estimate your glide angle and its resulting distance, you can judge how much maneuvering is possible to safely reach a given spot on the ground during an emergency landing.
Here you go, Liz.
Thanks.
You're welcome. Say, Liz, I understand you're a pilot.
That's right. I'm also a flight instructor.
Well, now that sounds interesting. What exactly does an instructor do?
Well,
As flight instructors, we have all heard this question at one time or another. And it's not an easy question to answer. Stated simply, we teach people how to fly. At first, these images may come to mind. On the other hand, there are a lot of CFI activities that go beyond the Learn to Fly category. While most people associate training activity with students seeking initial certification, there are a wide variety of specialized instructional services that we can also provide. These services may include regional and local checkouts, instructing an aircraft with conventional gear, checkouts in high-performance airplanes, multi-engine checkouts, and high-altitude training. This presentation introduces some general guidelines that apply to most checkouts, but also focuses on some additional factors which are unique to each type of training. Developing an outline for specialized instruction will help you provide comprehensive checkouts. One way to do this is to expand on a basic lesson plan format, or for transitions to other aircraft, the FAA provides a sample training plan in Advisory Circular 61.98A. A transition syllabus prepared by the General Aviation Manufacturers Association, or GAMA, is also referenced in Advisory Circular 61.103. But before we take off, we need to stop and address a number of important factors relating to the training program for a specific checkout. Evaluating our own ability to provide comprehensive instruction is one consideration. Before providing specialized training, we should ask ourselves some specific questions. Am I qualified by regulation to provide this type of instruction? FAR 61.195 describes applicable limitations regarding instruction. Experience is another important issue. Do I possess the experience necessary to provide a comprehensive checkout in this airplane or in this region? We should be very familiar with the make and model of the airplane and its flying characteristics. Can we accurately explain specific systems and operating procedures to the pilot? How recently have I flown the aircraft, reviewed the information, operated in the area? If we have the experience but have not put it to use lately, we may want to review the material before we teach it to someone else. The next step is to obtain some specific information from the pilot to help tailor the training to the individual. Find out about the pilot's flying background, including the certificates and ratings held, number of hours logged, experience in different airplanes, or operations at specific airports. If the pilot has not received any training recently, a review of basic procedures or subjects may be necessary before you introduce new material. Finally, the pilot's intention regarding the checkout is an important consideration. Will the pilot be flying frequently, in the local area or cross-country? Is the pilot considering any additional training? It is also important to know if the pilot is a flight instructor intending to provide instruction in the local area. Using the information provided by the pilot, determine if specific training or endorsements are required by regulation for the pilot to act as PIC of the airplane. It is important to brief the pilot on materials to review prior to the checkout, such as the pilot's operating handbook or information about the local flying region. This initial preparation will make the training more productive and enable you to focus on subject areas most valuable to the pilot. For an airplane transition, suggest that the pilot take time to sit in the cockpit and become familiar with the location of the instruments and equipment. In preparation for the flight portion of the checkout, you will need to determine what operations to cover and if regulations require proficiency in particular maneuvers. For example, if the pilot does not hold a category and class rating for the airplane and intends to solo, FAR 61.31 states that the pilot must have received flight instruction in the operations required for the first solo. The pilot should be aware of your expectations and the time it will take to complete the checkout. An initial evaluation flight may help in accurately estimating the hours that will be needed. To evaluate the pilot's performance during the checkout, consider using the standards listed in the PTS that apply to the certificates and ratings the pilot holds. These basic guidelines for preparing your instruction apply to most specialized services. Now let's look at types of specific checkouts and discuss the subject areas unique to each. A regional or local checkout is a service you can provide to a pilot who moves to a different area or will be operating out of an unfamiliar airport for an extended period of time. Flying environments vary greatly due to terrain, weather patterns, airspace, and traffic considerations. In addition to familiarizing the pilot with the local airport or region, there are other factors to consider in providing this type of checkout. For example, more than one goal can be accomplished during a local or regional checkout. You can suggest options to the pilot which will make the checkout more productive. A biennial flight review or airplane transition training may be combined with this checkout, or a complete mountain checkout may be appropriate for the area. The pilot may want to begin training for an additional rating or feel the need to review specific subjects or maneuvers. In addition, it may be necessary to point out local practice areas or the availability of practice instrument approaches if the pilot is a flight instructor. In preparation for the flight, it is important to explain how the area's climate and elevation will affect the airplane's performance. The pilot should calculate performance for the airplane based on local conditions. This is necessary regardless of the area. Many times the focus is placed on the decrease of performance when training pilots transitioning from low elevation to high elevation airports. Don't forget that an increase in performance at lower elevations or cooler temperatures may also be unfamiliar to pilots if they are accustomed to flying at higher elevations. Calculating takeoff and landing distances may help reassure the pilot that what appears to be a very short runway is sufficient in length. Also, the pilot may not be aware of the increase in climb performance and have a tendency to overshoot the desired level-off altitude. You can also point out that a richer mixture may be required and fuel burn will increase with flight at lower altitudes. Regardless of the pilot's previous experience, it is essential to review the performance charts in the pilot's operating handbook. If the pilot has been operating at one airport for an extended period, it may have been some time since the pilot analyzed performance data. Of course, the pilot will need to become familiar with the terrain features and airspace in the area. While studying the sectional for the region, it may be appropriate to review the symbols and definitions on the chart. Operating requirements for specific classes of airspace in the area may also need to be covered. If the pilot is instrument rated, a discussion of the en route, arrival, approach, and departure procedures for the area is recommended. To help the pilot feel more comfortable in the new surroundings, take some time to point out specific features of the airport, such as maintenance facilities, where to purchase fuel, and the location of wind indicators on the field. During the flight portion of the checkout, you can familiarize the pilot with local operating procedures and include any additional training as necessary. In addition to the regional or local checkout, a checkout in a specific aircraft is another useful instructional service. As pilots gain experience, the opportunity to transition to new and unique airplane types provides an exciting challenge. If you do not have experience in a particular airplane, you may need to receive a complete aircraft checkout yourself prior to checking someone else out. This will help in becoming thoroughly familiar with the aircraft systems, limitations, and specific operating characteristics, and better prepare you to provide comprehensive training. The transition to a conventional gear or tailwheel aircraft is a good example of a situation where such a checkout would be required. Gaining experience in conventional gear airplanes enhances your qualifications and expands your instructing opportunities. Because of the unique operating characteristics of tailwheel aircraft, a specific logbook endorsement to act as PIC in a tailwheel airplane is required by FAR 61.31. Although only one logbook endorsement is required, a checkout for each make and model of tailwheel is recommended due to differences in operating characteristics for individual aircraft types. For example, familiar equipment, such as an electrical system, may not exist in older aircraft. Seldom used procedures such as hand propping may have to be reviewed. Also, many tailwheel aircraft lack gyroscopic attitude and heading indicators or radio equipment. Another change may be in the aircraft controls. A stick may be used instead of the more familiar yoke configuration. During the checkout, you should note any characteristics that may affect how you will instruct in the aircraft. For example, in airplanes equipped with tandem seating, there may be reduced visibility from the rear seat, and communications between you and the pilot may be difficult due to high noise levels. In addition, there may be incomplete instrumentation or aircraft controls for the rear seat. Because the regulations require competency in normal and crosswind takeoffs and landings, wheel landings, and go-around procedures, these operations should be the focus of the tailwheel checkout. Mastering takeoffs and landings requires understanding of several unique features of the tailwheel airplane. For example, in gusty or crosswind conditions, the tailwheel airplane has an increased tendency to weather vane into the wind in comparison with nosewheel airplanes. This occurs due to the greater surface area behind the main gear. One consideration during takeoff is the tail lifting off the runway first. If the tail is raised too quickly, the airplane will react as if a force is exerted on the rotating propeller, and gyroscopic precession will cause a pronounced left-turning tendency. During the landing, it is important that the elevator control is eased fully back to hold the tail wheel on the ground. If the tail wheel is not held on the ground during touchdown, the airplane may become airborne again. This occurs due to increased lift produced by the higher angle of attack as the tail is lowered to the runway. Another unique characteristic of tailwheel aircraft is the location of the center of gravity behind the main wheels. This feature increases the difficulty in maintaining directional control, especially in the after-landing role. The CG location creates a tendency for the airplane to swerve further and further out of runway alignment once it is displaced. If positive directional control is not maintained with the rudder, a ground loop may be the result. Tailwheel training also introduces new procedures such as the wheel landing used in strong or gusty winds. This type of landing increases controllability by allowing the airplane to touch down at a higher airspeed and a lower angle of attack. In addition to becoming familiar with a different aircraft, a tailwheel checkout requires learning new techniques and provides an opportunity to increase flying skills. Having experience in conventional gear aircraft enables you to provide this specialized service to other pilots. As instructors, we can understand the importance of possessing sufficient experience before we are qualified to give safe and comprehensive instruction in a specific airplane. With that in mind, let's take a look at some additional opportunities for aircraft checkouts. The high-performance checkout is one more service you can furnish that will increase a pilot's knowledge, skills, and experience. FAR 61.31 defines high performance as an airplane that has more than 200 horsepower or that has retractable landing gear, flaps, and a controllable propeller. An endorsement is required to act as PIC of an airplane that meets either of these specifications or both. For example, if the pilot receives a checkout in an airplane that has retractable landing gear but does not have over 200 horsepower, a general endorsement stating competency in high-performance airplanes is provided. A second endorsement is not required by the regulation if the pilot then chooses to act as PIC of an airplane that has over 200 horsepower. The reverse is also true. However, it is important to explain to pilots that checkouts in both types of airplanes are highly recommended to ensure comprehensive knowledge of aircraft systems and safe operations. Procedures involving new and increasingly complex systems may be difficult at first for the pilot transitioning to a high-performance airplane. You can help to make the transition easier by discussing the new systems completely. The operation of the constant speed propeller control is usually emphasized during a high-performance checkout, but many pilots fail to fully understand how the system actually works to control RPM. You can explain that propeller designs vary in different aircraft. It is important that pilots have knowledge regarding the principles of constant speed propellers and should review the pilot's operating handbook for the aircraft. For example, most constant speed propellers in light aircraft maintain a preset blade angle by use of a governor. The governor either meters oil pressure to or allows oil to drain from the propeller cylinder to maintain the proper blade angle for constant speed operation. In certain propeller designs, an addition of oil pressure directed to the propeller piston increases the blade angle and decreases RPM. A complete loss of oil pressure in the prop hub system causes the blades to move to low pitch, resulting in high RPM. This provides the benefit of having maximum power available as long as the engine is running. In other systems, the opposite is true, and a complete loss of oil pressure in the propeller hub will create a low RPM situation. This system is valuable in multi-engine airplanes and allows feathering of the propeller when an engine loss occurs. The pilot should also understand the relationship between manifold pressure and RPM and know how to determine proper power combinations. Retractable landing gear introduces a new set of operating procedures, and learning how the system works will help the pilot understand gear operating limitations. The retraction or extension of the landing gear may be actuated electrically or hydraulically. Some systems combine electric and hydraulic components. After the pilot has studied the pilot's operating handbook, you can reinforce understanding with oral questioning. For example, if the gear is hydraulically actuated and a loss of hydraulic fluid occurs, what is the first indication of a problem? What position will the gear be in if all the fluid is lost? Will it stay retracted? Partially extend? Extend fully under its own weight? Gear warning indicators are not standardized. Some systems have indications for a retracted position, while others indicate when the gear is in transition. A complete understanding of how the manual extension system operates is also necessary. In addition to introducing unfamiliar equipment, a comprehensive review of all the systems in the airplane is appropriate if the pilot lacks basic systems knowledge. Be aware that the pilot may have difficulty adjusting to the faster speeds and increased performance of the airplane. The effects of power or configuration changes may seem exaggerated at first. Learning new procedures and operating complex systems increases the workload and may cause the pilot to feel rushed or behind the airplane. The use of checklists while thinking and planning ahead will make the transition easier. A good ground discussion of the systems and operating procedures prior to the flight will also smooth the pilot's transition. The next step for pilots who have acquired extensive experience in high-performance singles may be a multi-engine rating. In other cases, pilots who are multi-engine rated but have not flown a twin recently or wish to transition to a different make and model may require a full multi-engine checkout. The addition of a multi-engine class rating to a pilot's certificate is covered by FAR 61.63. It requires instruction in a multi-engine airplane in operations appropriate to the pilot certificate held. The operations to be covered are found in the appropriate practical test standards. At the completion of training, you must provide a logbook endorsement certifying the pilot's competency. According to FAR 61.195, you must hold a multi-engine class rating on your pilot and flight instructor certificate, and have at least 5 hours of experience as pilot in command in the make and model of multi-engine airplane before providing this instruction. The multi-engine checkout may include a review of the pilot's general knowledge of systems and aerodynamics, but many of the subjects to cover will be specific to multi-engine airplanes. For example, the pilot will need to understand the meaning of several V speeds, such as VYSE and VMC. Performance data, including accelerate, stop, and accelerate go distances, and systems unique to the airplane can be discussed using the pilot's operating handbook as a guide. And of course, engine out characteristics and procedures will need to be covered extensively. Prior to the flight portion of a multi-engine checkout, the pilot will benefit from an extensive discussion of the factors affecting directional control and engine out performance. You can begin this discussion by defining VMC and pointing out that the published VMC for an airplane occurs only under a specific set of conditions. The pilot needs detailed knowledge of the many variables that will affect controllability in an engine-out situation. Explain that controllability is not the only concern when an engine quits. Climb performance is drastically reduced in an engine-out situation. Point out that an airplane can lose 80% or more of its performance after an engine loss. For example, if a particular light twin climbs at 1,860 feet per minute with both engines operating, it may climb at only 190 feet per minute on one engine. The loss of performance in this case is close to 90%. By examining various aircraft configurations under specific conditions, you can explain to the pilot how each factor affects controllability and performance after an engine loss. One way to begin your discussion is to examine the factors listed in aircraft certification standards under FAR 23.149. The published VMC may not exceed 1.2 times the stall speed at maximum takeoff weight with the maximum available takeoff power or thrust on the engines. The most unfavorable center of gravity. The airplane trimmed for takeoff. The maximum sea level takeoff weight or lesser weight necessary to show VMC. The airplane in the most critical takeoff configuration with the propeller controls in the takeoff position and landing gear retracted. And the airplane airborne and ground effect negligible. Manufacturers may also establish up to 5 degrees of bank to determine VMC. The 5-degree bank is a good example to start with. You can explain the characteristics of the airplane without the bank to help the pilot understand the importance of establishing the bank after an engine failure. If the pilot maintains directional control with the rudder but does not establish the bank, the airplane will be in a side slip. By attaching a yaw string to the airplane, you can provide a vivid illustration of this fact to the pilot in flight. This side slip condition will add to the problem of controllability by causing the relative wind to push against the left side of the vertical stabilizer and fuselage, which will increase the yaw toward the dead engine. The side slip also decreases the rudder effectiveness by preventing some of the relative wind from reaching the rudder. And the airflow that does reach the rudder contacts the control surface at a smaller angle. Aside from increasing the actual VMC of the airplane, a side slip also increases drag, which will result in reduced performance. By establishing the precise amount of bank to create a zero side slip condition, the pilot will increase performance and controllability and decrease actual VMC. Less than a 5-degree bank may provide the best controllability and performance. You may recommend that the pilot initially establish a 5-degree bank and then reduce the bank slightly to determine if a smaller bank angle will have more positive results in performance. In addition to factors listed in the certification regulation, conditions to include in your discussion are the effects of density altitude, airspeed, extension of flaps, and benefits of feathering the propeller. One of the important goals of multi-engine training is for the pilot to obtain a complete knowledge of how specific factors affect controllability and performance in engine-out situations. Becoming proficient in high-performance single-engine and multi-engine airplanes also allows a pilot to operate at increasingly higher altitudes. Training in high-altitude flight is another opportunity for providing specialized instructional services. FAR 61.31 requires specific ground and flight training for a pilot to act as PIC of a pressurized airplane that has a service ceiling or maximum operating altitude, whichever is lower, above 25,000 feet MSL. A logbook endorsement certifying satisfactory completion of the training is also required. This training may not be mandatory for pilots who have specific qualifications that are outlined in this regulation. This also means that to provide the required high-altitude flight instruction to a pilot, you need to meet the requirements of this regulation as well. The regulation lists specific topics that must be covered during ground training, such as high-altitude aerodynamics, high-altitude meteorology, physiology of flight at high altitudes, including hypoxia and other high-altitude sicknesses, use of supplemental oxygen, time of useful consciousness, and knowledge of decompression. In addition, the pilot must receive flight training in an airplane or simulator as described by the regulation. This training includes cruise flight operations above 25,000 feet MSL, emergency procedures associated with rapid decompression, and emergency descents. Advisory Circular 61.107 provides an outline and a textual description of relevant subject areas to help you prepare for high-altitude instruction. The FAA actually recommends this training for all pilots who operate at altitudes above 10,000 feet MSL. To generate interest in high-altitude training, you can suggest that the pilot attend a physiological training program to learn more about the problems associated with reduced atmospheric pressure at high flight altitudes. These programs include a high-altitude flight in an altitude chamber where pilots can learn to recognize the onset of hypoxia by understanding their individual reactions to it. Applications for this training can be obtained from your local Flight Standards District office. If you have not experienced this physiological training yourself, participation in this type of program will greatly increase your instructional knowledge. To introduce high-altitude flying, you can expand upon the pilot's general background knowledge of aerodynamics, meteorology, and physiology. Some topics that you present may be new to the pilot. Pressurization is one subject that may be unfamiliar to a pilot seeking a high-altitude checkout. It is important for the pilot to understand how the specific pressurization system and oxygen equipment in the airplane operates. For example, in most pressurized light twins and singles, pressurization is supplied to the cabin from the turbocharger's compressor or from an engine-driven pneumatic pump. The cabin altitude is manually selected and can be monitored by reference to a gauge which indicates the pressure difference between the cabin and ambient altitudes. Each aircraft has a maximum differential between cabin and ambient altitudes that the pressurized section of the aircraft can support. Decompression can occur due to a system malfunction or results from structural damage to the aircraft. Due to the rapid drop in temperature and the change in relative humidity, fog will often form during a decompression. The human body will also be affected. A sudden low pressure outside the lungs will cause air to escape through the nose and mouth. Differential air pressure on either side of the eardrum will automatically equalize. Other hazards include exposure to wind blast and extremely cold temperatures. The pilot should be aware that decompression of a small volume cabin is more hazardous than a large one. Typically, a small aircraft can be expected to decompress 10 to 200 times faster than a large aircraft. A Learjet with a cabin volume of 265 cubic feet will decompress 223 times as fast as a Boeing 747 with a cabin volume of 59,000 cubic feet. An explosive decompression, which occurs in less than half a second, is dangerous and can cause lung damage. If a decompression occurs, pilots should understand what corrective action to take. Supplemental oxygen should be used and a rapid descent should be initiated. These actions should be taken immediately to avoid the onset of hypoxia. While the high-altitude checkout may require the most extensive preparation on your part, coverage of required subject areas will benefit all pilots, not just those seeking the high-altitude endorsement. At the completion of any training program, you can point out to the pilot the importance of maintaining the newly acquired skills and knowledge. Emphasize the need for recurrent refresher training on a regular basis for maintaining the pilot's proficiency. As you can see, there are a wide variety of specialized services that you can provide to pilots. With proper planning, you can create valuable learning experiences for pilots and promote safety and proficiency. And you will have plenty to talk about when someone asks you about all the things a flight instructor does.
Warrior 257, hold north of Gill VOR on the 350-degree radial. Left turns 8,000.
Crusader 32 Charlie, cleared to land runway 29er right, wind 310, what's up?
King Air 17 Hotel cleared to the Evergreen Airport, Victor 15, that is filed. Maintain 7000, departure control frequency.
Mooney 43 Echo, turn right, heading 240, descend and maintain.
Seneca 90150 Zulu, maintain VFR conditions above 11000. Falcon 29er Echo, cleared to land runway 35 right, wind 3405, caution wing turbulence.
During your private pilot training, your flight instructor gave you the opportunity to control the airplane by instrument reference for brief periods of time. As you enter the world of instrument flight, you need to develop the knowledge and skills to fly the airplane on a continuous basis by referring solely to your instruments and gauges. When you enter the IFR environment, it's essential to know how the instruments work and to understand their limitations so you can properly interpret the information they display. To begin, let's review the basic flight instrument systems. You should remember from your private pilot training that the flight instruments are divided into two systems: gyroscopic or pedostatic. The gyro instruments include the attitude indicator, heading indicator, and turn coordinator, while the pedostatic instruments are the airspeed indicator, the altimeter, and the vertical speed indicator. Let's look closely at the gyro instruments. On most small airplanes, the gyros in the attitude indicator and heading indicator are vacuum driven, while the turn coordinator is electrically powered. By having different power sources for the individual gyros, you'll have backup information if one system fails. One of the main reasons a gyroscopic instrument is able to display its information is because of a principle called rigidity in space. Inside the instrument, a rapidly spinning gyro tends to resist the external forces produced as the airplane maneuvers around it. By having the gyro remain in a relatively fixed position, the aircraft's attitude can be measured in relation to the gyro. The turn coordinator also incorporates another principle called precession. Whenever your airplane's attitude changes, the pressures exerted by the external forces tend to make the gyros change their plane of rotation, or precess. The faster the change, the greater the pressures, and therefore the precession. The turn coordinator measures the precession of its gyro and indicates the rate of turn. However, precession is not always beneficial and can cause errors, which we'll discuss later. During VFR flight, you are able to maintain the aircraft's attitude by comparing references on the airplane to the natural horizon. During instrument flight, you no longer have that luxury. Now you must rely on the flight instruments for pitch and bank information. The one instrument which directly shows both pitch and bank is the attitude indicator. However, because of precession, the attitude indicator could give you erroneous indications. For example, if you accelerate rapidly, the instrument may indicate a slight climb. If your reaction is to lower the nose to return the miniature airplane back to level, your actual pitch attitude will be lower than that shown on the instrument. This will place your airplane in a descent unless you take corrective action. The opposite occurs when you decelerate rapidly. Here, the initial indication is that of a slight descent. Now let's review the heading indicator. The spinning gyro in the heading indicator is aligned with the vertical plane, allowing it to sense any changes in the airplane's vertical axis. The heading indicator is very susceptible to gyroscopic precession. As you maneuver the airplane, the external forces acting on the gyro cause the heading to drift very slowly. In this case, it is drifted 5 degrees. For this reason, you need to periodically realign it with the magnetic compass. Because the operation of the attitude and heading indicators relies on vacuum pressure, be sure to include the vacuum indications in your scan. The third gyroscopic instrument is the electrically powered turn coordinator. Although the miniature airplane looks like it is banking, it is only measuring the rate of turn or roll rate. It does not show angle of bank or pitch information. One of the most important uses of the turn coordinator is that it enables you to establish and maintain a standard rate turn, which is the rate you should use for most instrument maneuvers. With the wings of the miniature airplane aligned with the reference mark, you'll turn at a rate of 3 degrees per second. The second part of the turn coordinator is the inclinometer. Just as in VFR flight, the ball helps you maintain coordinated flight. Now let's re-examine the pitot-static instruments and look at their importance during your transition to the IFR environment. The basis for the functioning of the pitot-static instruments is differential air pressure. While the air pressure surrounding the airplane is vented to all three through a static port, only the airspeed indicator receives ram air pressure. This instrument measures the difference between the ram air and static air pressure and displays the result as an indicated airspeed. Knowing your relationship to terrain and obstructions would be virtually impossible at various times during your instrument flight without the information provided by the altimeter. As you learned during your private pilot training, the altimeter senses changes in the surrounding air pressure. Your mean sea level altitude is shown when you adjust the instrument to the correct local altimeter setting. If you didn't adjust your altimeter to the changing conditions, your actual height above sea level would be higher or lower than that indicated. Remember that as atmospheric pressure increases, your actual altitude is higher than that indicated. When the pressure decreases, your actual altitude is lower than indicated on the altimeter. To prevent the wrong indication, you should set your altimeter to the local altimeter setting. During instrument flight, air traffic control periodically provides you with the correct altimeter setting. The final pitot-static instrument is the vertical speed indicator. Although it is not required for instrument flight, you'll find that it's extremely useful for helping to control the airplane precisely in instrument weather. The VSI senses how fast the surrounding air pressure decreases or increases as you climb or descend, and displays the change as a rate in feet per minute. When a change in altitude occurs, the VSI immediately registers the trend of movement. It then stabilizes to show the actual rate. As an instrument pilot, you should be aware of the erroneous readings which can occur if the pitot-static system becomes blocked by ice, dirt, or even insects. If the pitot tube becomes blocked, two types of errors can occur with the airspeed indicator. If the air inlet is blocked but not the drain hole, the pressure in the line will vent out the opening, causing the indicator to drop to 0. However, if both openings are clogged while the static port remains open, air pressure remains in the line and the airspeed indicator now performs like the altimeter. As the airplane climbs from the altitude where the blockage occurred, the airspeed increases. Conversely, as you descend, the airspeed decreases. To help prevent blockages in the pitot system when operating in possible icing conditions, you should make sure the pitot heat is on if your airplane is so equipped. If the pitot tube remains open but the static system becomes blocked, the airspeed indicator still reacts to changes in airspeed. However, the indications are not correct. If you're operating at a higher altitude than where the system became blocked, then the airspeed reads lower than it should. Below the altitude, the airspeed indication is higher. The greater the altitude change, the greater the error. If the static system becomes blocked while you're changing altitudes, the altimeter freezes in place and the VSI returns to 0. If this occurs, you need to find an alternate source of static pressure. Many aircraft have an alternate static source. On a non-pressurized airplane, it is usually vented to the cabin area. If an alternate source is not available, you could, as a last resort, break the glass on the VSI. With the glass broken, you should consider any VSI readings unreliable. In both cases, the pressure inside the cabin is slightly lower than that surrounding the airplane. Therefore, the altimeter will read higher and the airspeed faster than normal. Because the flight instruments are so critical during IFR conditions, you should take extra care to ensure they are working properly. This includes making sure the static, altimeter, and automatic pressure altitude reporting systems have been inspected within the preceding 24 calendar months. During the pre-flight, visually inspect the static port and pitot tube for obstructions. Once inside the airplane, check that the wings are level in the turn coordinator, that there is fluid in the inclinometer, and that the ball rests in the lowest point. Then when you turn the master switch on, listen to the sound of the electrically driven gyros and make sure there are no abnormal noises. Once the instruments stabilize, continue your inspection by verifying proper alignment of the attitude indicator and turn coordinator. Check that the VSI is indicating 0. If it doesn't, simply apply the error to your in-flight indications. Set the altimeter to the current reported setting and make sure it reads within 75 feet of the airport elevation. Then verify that the airspeed indicator is reading 0. As you begin to taxi, check the heading indicator to verify directional changes during the turn. The turn coordinator should also indicate a turn in the same direction, with the ball shifted away from the turn. Prior to takeoff, make sure you've aligned the heading indicator with the magnetic compass. Then, as you're accelerating for takeoff, quickly glance at the instruments to verify that the gyros are not drifting and that the airspeed indicator is increasing at an appropriate rate. The world of instrument flight is a truly fascinating one. As you gain experience in flying by instruments and become accustomed to the information portrayed on the panel, you'll open up new horizons for your flight.
Attitude instrument flying is the technique of controlling your airplane by using the flight instruments rather than outside visual references. It involves establishing a precise attitude for a given power setting and then maintaining that attitude by reference to the flight instruments. When a change in the airplane's attitude is required, initially make the change by referring to the attitude indicator. Then scan the other instruments as needed for verification. For example, besides the attitude indicator, any change in bank is apparent on the heading indicator and turn coordinator. Pitch changes can be seen on the attitude indicator, altimeter, VSI, and airspeed indicator. Let's take a look at some of the basic maneuvers using instrument references, beginning with straight and level flight. For this maneuver, you need to control both heading and altitude. To maintain the desired heading, establish a wings level attitude on the attitude indicator. Then, monitor the bank instruments for any deviation. If you drift off your desired heading, adjust the attitude indicator to a bank angle that will correct the deviation. You should use a bank angle that equals the number of degrees of correction, as long as it doesn't exceed a standard rate turn. For example, if you're 10 degrees off your desired heading, you should use a bank of 10 degrees to get back on course. In straight and level flight, maintain altitude by establishing the appropriate pitch on the attitude indicator. Normally, the miniature airplane is aligned with the artificial horizon. However, if you increase the airspeed while maintaining level flight, the miniature airplane will be below the horizon. At slower airspeeds, it is above. After you've established level flight for a particular airspeed, you should reset the miniature airplane so it is on the horizon. After the correct attitude has been established, confirm level flight by referring to the altimeter, vertical speed indicator, and airspeed indicator. If your altitude starts to change, look at the VSI to determine the rate of the change. A small rate change will only require a minor correction. You should also check the airspeed indicator to see how the pitch change has affected the airspeed. If the airspeed is extremely fast or slow, you'll have to make a larger correction. When you have determined that a correction is necessary, stop the movement by adjusting the pitch attitude slightly. Then make the necessary adjustments to return to your desired altitude. Normally, if the altitude deviation is less than 100 feet, use a correction of a half bar width. If the deviation is greater than 100 feet, initially use a full bar width. Once the new pitch attitude is established, check the altimeter, vertical speed indicator, and the airspeed indicator to see that you have made the proper correction. Now let's take a look at turns. Most turns are performed at the standard rate of 3 degrees per second. As with straight and level flight, establish the bank using the attitude indicator. You can estimate the approximate bank by dividing your true airspeed by 10 and then adding 5. For example, if your true airspeed is 120 knots, you will be in a standard rate turn if your bank is approximately 17 degrees. You can verify that your turn is coordinated and that you're using the proper bank by referring to the turn coordinator. No matter what the airspeed, if the wing on the instrument is aligned with the mark and the ball is centered, you're in a standard rate turn. When established in the turn, the altimeter and VSI confirm your pitch attitude. If you observe a deviation, adjust the pitch on the attitude indicator and check the altimeter and VSI to see that you have made the proper correction. The airspeed indicator will directly indicate the need for a power change. During your instrument training, you will learn to make turns faster than standard rate. To do this, steepen the bank. As bank increases, the loss of vertical lift causes the aircraft to descend. To compensate, increase the pitch attitude and trim the aircraft. Scan the altimeter and VSI to confirm that your pitch adjustment is correct and that you're maintaining level flight. Since an airplane tends to slow down during a steep turn, you need to increase power to maintain airspeed. Remember to lead the rollout by 1/2 the bank angle. For example, if you're turning to 180 with a bank of 40 degrees, start your rollout at 200 degrees. As you begin the rollout, you need to reduce the pitch attitude and power to maintain level flight. Then retrim the aircraft. When changing altitudes in instrument flight, you should perform either a constant airspeed or constant rate climb or descent. To maintain a constant airspeed, initially adjust the pitch attitude of the airplane by referring to the attitude indicator. During this maneuver, you normally hold a constant power setting. However, if you desire to change the rate of descent or climb, you can vary the power. While performing the maneuver, monitor the airspeed indicator and make small adjustments in pitch attitude to maintain airspeed. Check your heading indicator and turn coordinator to verify straight, coordinated flight. Constant rate maneuvers are performed in a slightly different manner. In this case, the object of the maneuver is to establish a climb or descent at a constant rate. After establishing the approximate pitch and power settings using the attitude indicator and the throttle, verify the correct rate by referring to the vertical speed indicator. If a change occurs, you need to make an adjustment in the pitch attitude. With a constant rate maneuver, adjust the power to achieve the desired airspeed. Approaching your target altitude, use the 10% rule of thumb for leading your level off. In other words, if your descent rate is 500 feet per minute, start your level off 50 feet before your desired altitude. In IFR flight, you should be aware that because of spatial disorientation, you could get yourself into an unusual attitude. This usually occurs after you've been in a prolonged descending turn and then bring the airplane back to straight and level. This could result in a false sensation of being in a climbing turn in the opposite direction. When using instruments as your primary means of controlling the airplane, remember to trust your instruments. They are much more reliable than your senses, especially when there are no outside references. If you should observe a nose-high indication on the attitude indicator, a decreasing airspeed, a rapidly increasing altimeter, and a high climb rate on the VSI, you are in a nose-high, unusual attitude. Since preventing a stall is most important in this situation, you should immediately lower the nose while simultaneously adding power. If you are in a bank, you should roll the wings level. Another potentially dangerous situation occurs when the nose is too low. Here, excessive airspeed could lead to possible structural damage during the recovery. A nose-low indication on the attitude indicator, increasing airspeed, decreasing altitude, and a high descent rate on the VSI are all indications of a nose-low attitude. To correct this situation, simultaneously reduce power and roll the wings level. Then gently raise the nose to a level flight attitude. Flight instruments, like all mechanical things, are subject to malfunctions. Therefore, you need to know alternate sources for pitch, bank, and heading information if the main sources are inoperative. For example, suppose you notice that your aircraft's attitude indicator is showing a 5-degree bank to the right. However, the heading indicator is not moving. The turn coordinator indicates a left turn, which is confirmed by the magnetic compass. A check of the suction gauge indicates that there isn't sufficient vacuum to drive the gyros. If this happens, the indications on both the attitude and heading indicators are no longer reliable. To complete the flight, you'll have to use the other instruments. When flying partial panel, you must identify the inoperative instruments and omit them from your scan. If they become too distracting, you might find it helpful to cover the instrument faces. With the attitude indicator and the heading indicator no longer functional, your reference for bank information is now the turn coordinator. For pitch information, you must rely on your VSI, altimeter, and airspeed indicator. For heading information, use your magnetic compass. The compass, however, is susceptible to the forces of magnetic dip and acceleration errors and does not give reliable information during a turn. This necessitates the use of a timed turn to make a heading change. Remember, with the wing aligned on the turn coordinator, your rate of turn will be 3 degrees per second. You can use this figure to calculate how many seconds it will take to turn to a new heading. For example, let's say that you are on a heading of 270 degrees and want to turn to 180. That's a heading change of 90 degrees. At a turn rate of 3 degrees per second, it will take you 30 seconds to reach the new heading. After timing for 30 seconds, begin your rollout. When stabilized in level flight, read the magnetic compass. You may have to make small adjustments to get to the exact heading you desire. In this program, we have looked at some of the maneuvers you'll perform by reference to the flight instruments. Learning how to execute these maneuvers proficiently will greatly assist you when it comes time to start making instrument approaches.
During your VFR training, you learned several methods for keeping track of your position and navigating from one place to another. You learned how to use pilotage and dead reckoning. And you learned basic radio navigation skills using VOR and ADF. As you transfer to instrument flight, your knowledge and understanding of radio navigation must increase, since your outside visual references are replaced by instruments. The ability to visualize your position is one of the most important IFR skills you can develop. It makes IFR navigation much easier. With that in mind, let's review some of the basics of VOR navigation as they relate to IFR flight. We'll begin with this clearance from departure control.
Warrior 312, 5 miles northeast of Jackson VOR, intercept Victor 77 and resume your own navigation.
As you can see, it's always important to know where you are. To intercept the radial, the first thing you need to do is visualize your position in relation to where you want to go. In this case, you are to the east of Victor 77, which is the 020 degree radial from the VOR. With the VOR indicator set to the 020 degree radial, the CDI shows a full-scale deflection to the left. This means you are more than 10 degrees from the radial. To find out where you are, rotate the OBS until the needle centers with a from indication. In this situation, you're located on the 060 degree radial from the station. Now that you know what radial you're on, you need to choose a heading that will enable you to intercept the 020 degree radial. The angle of interception depends on several factors, such as your ground speed and proximity to the radial and navigational aid. A wide range of angles may be suitable. One possibility is to fly a 90-degree intercept to the 020 degree radial. In this case, you need to anticipate your turn onto the airway, since a 90-degree standard rate turn takes 30 seconds. Another choice is to intercept the radial at a smaller angle. For example, a 30-degree angle is commonly used for en route operations. For this intercept angle, you must maintain a heading of 350. As you approach the radial, the CDI helps you anticipate your turn onto the course. At standard rate, the 30-degree turn will take only 10 seconds, so the amount of lead is relatively small. Although the basics of VOR tracking and bracketing are the same for both visual and instrument flight, these skills need to be fine-tuned for IFR navigation. It is important to realize that, as you fly away from a VOR, a deviation from your desired course represents a greater lateral distance. Each dot represents a lateral distance of 200 feet for every nautical mile you travel away from the VOR. For example, at 5 miles from the VOR, a 1-dot deviation means you're about 1,000 feet away from the course. But at 30 miles, this same deflection places you about a mile off course. Another skill you need for IFR navigation is identifying an intersection that is based on VOR. Here, you identify Walto by the intersection of the airway and the 270 degree radial from Duncan VOR. One indicator is used to navigate along the airway. The other one is tuned to the Duncan VOR, with the OBS set at 270 and a from indication. When the needle centers, you are at the intersection. Another method for identifying an intersection, as well as keeping track of your position, is through the use of distance measuring equipment, or DME. The equipment on board your airplane transmits a radio signal to the selected ground facility. This triggers a response back to the aircraft, where the time lapse is translated into your distance and time from the station, as well as your ground speed. Remember that DME measures the slant range distance between your airplane and the ground station, rather than the horizontal distance. Although the slant range error is negligible at long distances and low altitudes, it may become significant at high altitudes when you're close to the station. For instance, if you pass over the station at 12,000 feet AGL, the DME will show approximately 2 miles instead of 0. Now, let's take a look at an instrument that combines the features of the VOR and the heading indicator. The horizontal situation indicator is gaining popularity because of the abundance of navigation information it provides in a pictorial display. The compass card provides you with headings, just like a normal heading indicator. The course selection knob functions like an OBS and moves the course arrow to your chosen radial. The lateral deviation indicator is similar to the CDI and senses your position with respect to the selected radial. The ambiguity indicator functions like the to from indicator and shows whether the selected radial will take you to or from the station. The airplane symbol in the center of the HSI represents your horizontal situation in relation to the nav aid. A glide slope indicator shows your position relative to the glide slope. You'll learn its importance later on when you practice instrument approaches. To see how easy the HSI is to interpret, assume you are southwest of a VOR on a heading of 360 and want to intercept the 270-degree radial and fly inbound to the station. The first thing you do after tuning and identifying the station is to set the inbound course of 090 degrees. Notice the ambiguity needle shows that this course is to the VOR. With an HSI, it is easy to visualize your position. The relationship between the miniature airplane and your intended radial is shown by the lateral deviation needle. You know that you're flying toward the radial at a 90-degree angle. Choosing an intercept angle is simple with an HSI since it provides a visual presentation of your aircraft heading and your selected course. Let's assume you want a 45-degree intercept. After turning the airplane to 045 degrees, notice how the instrument shows your angle as well as your new heading. As you approach the radial, the needle will begin to move towards center to signify that you're nearing the course. You can gradually shallow the angle depending on your rate of closure to smoothly intercept the new course. You might have to adjust your heading slightly to compensate for the wind. Let's now look at the benefits of an automatic direction finder. ADF has a wide variety of uses in the IFR environment. You can use it to receive weather information and to provide position orientation during en route flight and instrument approaches. Since the navigation signals are not limited to line of sight, you can receive them at lower altitudes and greater distances. Let's take a moment to review how bearing information is given. On a fixed card ADF, you determine your magnetic bearing to a station by adding your magnetic heading to the relative bearing. In this case, the magnetic heading is 030 and the relative bearing is 090. This produces a magnetic bearing to the station of 120 degrees. Your text covers the fixed card ADF in detail. With a movable card, you can dial in your magnetic heading and the needle will point directly to the magnetic bearing. To demonstrate how to visualize your position and navigate with ADF, assume you're on an easterly heading and you want to intercept the 360-degree bearing to the NDB and track inbound. After identifying the station, you find that your present position is on the 020-degree bearing to the station as shown by the head of the bearing pointer. Rather than use a 90-degree angle, you decide to turn left and intercept the bearing at 30 degrees. Your heading in this case is 030 degrees. By setting your magnetic heading under the top index, you can use the head of the bearing pointer to show your position in relation to the bearing. When it indicates 360, you have reached the bearing. In actual practice, you should begin your turn just before you intercept the bearing. This reduces the possibility of overshooting the desired course. Since the ADF does not automatically provide a wind correction angle as a VOR does, let's review the bracketing procedures. In this example, you've drifted right of the 360-degree bearing to the station. The ADF is sensing a crosswind by pointing to 350. To regain the course, you apply a 10-degree correction into the wind and reset the ADF to match your heading. If your heading and relative bearing remain constant, you've corrected for the drift. but you will not intercept the 360-degree bearing. So, an additional correction is needed. In this case, you are using a 20-degree correction angle to regain the course. If you continue to keep the ADF heading aligned with your magnetic compass, you can verify that you have returned to the course when the head of the bearing pointer equals 360 degrees. To remain on course, use just enough crab to maintain this magnetic bearing. The last navigation instrument we'll look at is a radiomagnetic indicator. The RMI lets you continuously monitor your heading as well as your position from two nav aids simultaneously. While one needle indicates your magnetic bearing in relation to an NDB station, the other shows the magnetic bearing to a VOR station. To see how this instrument works, assume you're flying north along an airway on the 180-degree radial of a VOR. An intersection ahead of you on the airway is identified by the 090-degree bearing to an NDB. With an RMI, you can navigate along the airway with one needle while continuously monitoring the ADF pointer. When it points to 090, you are at the intersection. As you continue northward, the bearing pointers provide a perpetual display of your position relative to the two stations. And instrument interpretation are the foundation upon which all instrument flying is based. Mastering these skills will enable you to efficiently operate in the IFR environment.
The departure procedure you use during an IFR flight varies from airport to airport. Sometimes it may be as simple as a climbing turn to your intended course. At other times, it may involve a complicated set of courses, altitudes, and vectors. Therefore, before making an IFR departure, you should acquaint yourself with the procedures which are available at your airport. By regulation, before any IFR flight, you must check the en route weather and the weather at your destination and departure airports. For commercial flights operating under Part 121, 125, or 135 of the Federal Aviation Regulations, certain visibility requirements must be met before a takeoff is allowed. While these minimums are not required for flights conducted under Part 91, they are good guidelines for you to follow. For aircraft with one or two engines, the standard visibility minimums for takeoff are 1 statute mile. Because some airports have obstructions such as rising terrain, a minimum ceiling, as well as an increase in the visibility, may be required. If the minimums are higher than standard, they will be noted on NOS charts by a triangle symbol enclosing a T. This symbol is found in the information box and can also indicate that departure procedures are published. To determine the exact minimums, you need to refer to the IFR Takeoff Minimums and Obstacle Departure Procedures section in the front of the Terminal Procedures booklet. For example, at Daytona Beach, the takeoff minimums for runways 7 right, 16, 25 left, and 34 are a 300-foot ceiling and 1 mile visibility. Jeppesen prints this information on the airport chart. Since the takeoff minimums are normally based on visibility, let's look at the various types which are reported at an airport. Prevailing or tower visibility is the greatest distance a weather observer or tower controller can see throughout at least 1/2 the horizon circle. It is measured in statute miles or fractions of miles. Runway visibility value, or RVV, is the distance down the runway that you can see unlighted objects or lights of moderate intensity. This value is generally derived from an electronic measuring device and is listed in miles or fractions of miles. When available, RVV is used instead of prevailing or tower visibility. The most accurate reading of visibility along a specific runway is the RVR, or Runway Visual Range. This value is based on measurements from transmissometers located near the runway and relates the horizontal visibility in hundreds of feet. An RVR value of 12 means that the visibility is 1,200 feet. Since the visibility may vary from one runway to another and at different portions on the same runway, especially at larger airports, the RVR value should be used only for the specified runway. Once you have determined that the weather will allow you to make a takeoff, you need to consider what type of departure procedure you're likely to use. When departing an airport, you must climb at a rate of at least 200 feet per nautical mile. This allows at least 48 feet of obstacle clearance for every nautical mile you travel. If obstacle clearance requirements are not met, a textual or graphic departure procedure will be published. These departures are designed according to the criteria established in the United States Standard for Terminal Instrument Procedures, abbreviated TIRPS. NOS publishes the obstacle textual departure procedures with the takeoff minimums at the beginning of the Terminal Procedures booklet. Jeppesen prints them on the airport charts. Departures from airports near large metropolitan areas are usually conducted under radar coverage. A series of heading assignments, called vectors, are provided to transition you from takeoff to the en route portion of your flight. In these cases, the tower generally gives you an initial heading to fly. A short time after liftoff, the tower will instruct you to contact departure control. After changing to the departure frequency, your initial call should include your ID, current altitude, and the altitude to which you're climbing.
Departure Cessna 52241, 2,500, climbing to 5,000.
By stating your current altitude, the controller can verify the accuracy of your Mode C transponder.
Cessna 241, roger, radar contact.
Radar contact is used by the controller to let you know that your aircraft has been identified. However, it is your responsibility to maintain adequate obstacle clearance until the controller issues you a vector or other instructions. Departure control will then give you specific headings to fly in order to intercept your clearance route. Once the final vector has been given, the controller will tell you to resume own navigation. This phrase means that the controller now expects you to navigate using your own equipment. It does not mean that your flight is no longer in radar contact. When departing an airport without an operating control tower, some additional procedures may apply. For example, you might use a ground communications outlet. You may be issued a clearance void time. ATC uses this procedure to reserve airspace around the airport. If you do not depart before this time, your clearance will be canceled. When climbing to your assigned altitude, ATC expects you to climb at the optimum rate for your aircraft until you're within 1,000 feet of your target altitude. Then, slow your rate to 500 to 1,500 feet per minute until you begin to level off. If you cannot maintain at least 500 feet per minute throughout the climb, you must notify ATC of your actual rate. In addition to providing obstacle clearance, at busier airports, instrument departure procedures, or DPs, expedite the flow of air traffic by reducing the length and complexity of issued clearances and by cutting down on pilot-controller communications. As with any IFR departure, DPs also assure adequate obstacle clearance. Some instrument departure procedures contain specific performance requirements in order to maintain adequate obstacle clearance. You should always review the graphic instrument DP chart you're planning to use to verify that your aircraft can comply with the required performance criteria. If you cannot meet these requirements, you should request no DP on your flight plan. A graphic instrument departure procedure requires you to fly a specific route and altitude combination after takeoff. For example, let's take a look at the Gorman transition of the Merrick 3 departure at Bakersfield, California. To fly this pilot nav departure procedure, first look at the takeoff information for the runway in use. In this case, as soon as you take off from runway 12 left, you're required to make a right turn to a heading of 240. From there, the procedure calls for you to intercept the 196-degree radial of the Shafter Vortac and proceed to Merrick intersection. To reach Gorman, fly the 109-degree radial of the Avenel Vortac until you intercept the 328-degree radial of the Gorman VOR. Then fly direct to Gorman VOR. From this point, proceed according to your flight planned route, unless otherwise instructed. Notice that Ninty intersection has a minimum crossing altitude of 8,800 feet for the Gorman transition. If you were using the Lake Hughes transition, the minimum crossing altitude for Ninty would be 6,000 feet. These altitudes are necessary to achieve the minimum altitudes along the transition routes. As you have seen, an instrument departure procedure can take many forms and is frequently changed. Because of this, it's important that you understand the procedure and its requirements on you and your aircraft before you take off.
Throughout most of your IFR flights, you are usually followed by some segment of the air traffic control system. On many cross countries, your flight will be handed off from departure control to an air route traffic control center. This handoff is usually accompanied by instructions which include the name of the next facility, the frequency, and any other pertinent information.
Cessna 241, contact Los Angeles Center on 127.1 at Lesty intersection.
Cessna 241, Los Angeles Center on 127.1 at Lesty.
After you have established communications and have been radar identified by the next controller, you can expect normal radar services until the controller informs you that radar service has been terminated or radar contact lost. While in radar contact, there are certain reports listed in the Airman's Information Manual which you should make to ATC. For example, you should let ATC know when you are leaving an assigned altitude for a newly assigned altitude, and any time you're changing altitudes when VFR on top. Other reports include a change in the average true airspeed of 5% or 10 knots, whichever is greater. You should also notify ATC if you cannot maintain a climb or descent of at least 500 feet per minute. Other reports include the time and altitude when you reach a holding fix or point to which you have been cleared, leaving an assigned holding fix or point, and initiating a missed approach. In addition to the reports listed in the AIM, regulations require you to report any navigational approach or communications equipment malfunction while in flight. You are also required by regulation to report any unforecast weather encountered and any other information relating to the safety of flight to an ATC facility. There are other reports which you need to make when not in radar contact. For example, you should report a new estimated time of arrival if it changes by more than 3 minutes. You should also report the final approach fix inbound on a non-precision approach, or the outer marker, or the fix used in lieu of it on a precision approach. In order for ATC to follow your progress and keep you separated from other traffic in a non-radar environment, regulations require that you supply position reports. On an en route chart, a compulsory reporting point is indicated by a solid triangle like the one at Pulaski VOR. A report at a non-compulsory fix, such as Doily intersection, is only required when it is requested by ATC. The IFR position report that is required over these points should include your identification, position, time, flight altitude, the name and ETA over the next reporting point, and the name of the following reporting point. Even if you're in radar contact, you should always keep track of your flight's progress, because you never know when radar contact may be lost or terminated, and you'll have to start making position reports. To make sure you are flying on your assigned altitude when below 18,000 feet MSL, adjust your altimeter to the current setting reported by a station within 100 nautical miles. At or above 18,000 feet, set the altimeter to 29.92. Your altitude is now read as a flight level. For example, 31,000 feet is flight level 310. When you're flying IFR in uncontrolled airspace, you should use the hemispheric cruising altitudes. Below 18,000 feet MSL, use even 1,000-foot altitudes for westbound flights and odd 1,000-foot altitudes for eastbound flights. Although the altitude for your flight in controlled airspace is assigned by ATC, it often follows these cruising altitudes. At or above 18,000 feet, you will be assigned even or odd flight levels. As you're approaching your destination, ATC will issue you a descent clearance.
Cessna 241, descend and maintain 10,000.
This clearance gets you to an altitude where you can begin the approach procedure. There are times when your flight must be delayed for reasons such as traffic separation or approach sequencing. In these cases, ATC issues you a holding clearance and has you enter a holding pattern. If the holding pattern is charted, the clearance contains the direction from the fix, the name of the fix, an instruction to hold as published, and an expect further clearance time.
Cessna 52241, hold northeast of Matin intersection as published. Expect further clearance at 1533.
If there is no published holding procedure, ATC issues a more descriptive instruction. All the items in the previous clearance are given except for hold as published. Instead of this phrase, you receive a description of the course line you're to hold on, the length of the legs if appropriate, and the direction of the turn if you're to use a non-standard holding pattern. While in a standard holding pattern, all turns should be made to the right. These turns should be limited to a standard rate or 30 degrees, whichever is less. Non-standard patterns use the same procedures. However, now you make the turns to the left. To help you understand this procedure, let's look at some of the parts of a holding pattern. The inbound leg takes place along the holding course. When you reach the fix, turn to the outbound leg. After the proper time or distance, turn to re-intercept the inbound leg. The side of the course where the holding takes place is referred to as the holding side. Unless specifically stated in your clearance, the length of each holding leg is determined by time. The timing of each inbound leg is 1 minute when you're holding at or below 14,000 feet, and 1.5 minutes when holding above 14,000 feet. For simplicity, let's use 1-minute legs for the rest of the discussion. In a no-wind condition, the inbound and outbound legs will take the same amount of time. Since a no-wind condition is rare, you need to make adjustments on the outbound leg to achieve the proper inbound timing. For example, suppose on your initial timing it took you 1 minute 15 seconds to fly inbound. To correct this situation, you should try flying outbound for 45 seconds before turning inbound. This should now make your inbound leg approximately 1 minute in length. A crosswind also requires an adjustment. However, if you use the same amount of correction on the outbound leg, you will overshoot the course following your turn inbound. To compensate, you must triple the correction you used on the inbound course and apply it to the outbound heading. This should place you near your inbound course when you complete the turn. With some exceptions, the holding speed for propeller and jet aircraft is 200 knots indicated airspeed, up to 6,000 feet MSL. Above 6,000 feet to 14,000 feet, the maximum holding speed is 230 knots. And above 14,000 feet, the maximum holding speed is 265 knots. In some cases, holding speed may be restricted to 175 knots or 210 knots indicated airspeed. When this is the case, you will see an icon or note on the chart depicting that holding speed. If the indicated airspeed of your airplane exceeds the maximum holding speed, you should reduce it at least 3 minutes before your ETA at the holding fix. To minimize the amount of maneuvering you have to do, the FAA recommends that you enter a holding pattern by one of 3 methods. Use of these procedures makes the entry simpler and reduces the possibility of penetrating unprotected airspace. The area around a holding fix is divided into sectors, which are formed by an extension of the inbound holding course and a line which crosses the course at an angle of 70 degrees, as measured from the inbound course on the holding side. This line, along with the extended holding course, forms 2 70-degree sectors and 2 110-degree sectors. The 2 sectors that border the holding course are combined to form a 180-degree sector. If you're approaching from the 180-degree sector and you're entering a standard holding pattern, a direct entry is suggested. This means that after crossing the fix, simply turn right to the outbound heading. When approaching from within the 110-degree sector, a parallel entry is appropriate. As you cross the fix, turn to the outbound heading and parallel the inbound course on the non-holding side. After 1 minute, turn left and return to the holding fix or intercept the inbound course. Use a teardrop entry if you're entering the holding pattern within the remaining 70-degree sector. In this case, after crossing the fix, turn to a heading 30 degrees to the holding course on the holding side. After the appropriate time, turn back to intercept the holding course. When you're cleared into a holding pattern, the easiest method of determining the proper entry is to use your heading indicator and mentally visualize in which sector the inbound holding course falls. To do this, assume the holding fix is in the middle of the heading indicator. Then mentally extend a line from the fix to the top of the instrument, and another line from 70 degrees right to 110 degrees left. These lines now form the teardrop, direct and parallel sectors.
In this way, you can quickly visualize the type of entry you should use. For example, if the inbound holding course of a standard holding pattern is generally behind you as you arrive at the fix, you will probably use the direct entry. If the holding course is generally ahead and to your left, use the parallel entry. When the holding course is ahead and to the right, the teardrop entry is normally recommended. The same procedure can be used for a non-standard pattern. However, in this case, use left turns and reverse the parallel and teardrop entries. When leaving the holding fix, you should report it to ATC.
As traffic around an airport becomes more congested, procedures for sequencing aircraft to an instrument approach become necessary. One of the easiest ways for ATC to ensure an orderly flow of traffic is to assign an inbound aircraft a standard terminal arrival route, or STAR. It is important to follow arrival procedures carefully. With that in mind, let's look at a STAR for a flight into Phoenix Sky Harbor International Airport. As you're approaching Blythe VOR at 12,000 feet, Los Angeles Center issues the following clearance.
Cessna 241, cleared to Phoenix Sky Harbor Airport via the Blythe to arrival. Maintain 12000, contact Phoenix approach at Salome on 120.7.
ATC can assign you a STAR even though you have not requested the procedure, unless you have indicated no STAR on your flight plan. If you accept the clearance, you must have the charted procedure or at least an approved textual description of the STAR. Let's review the Blythe 2 arrival. This STAR begins at the Blythe VOR. From there, you'll follow the 082-degree radial to Salome intersection. Then you'll proceed inbound on the 285-degree radial of the Gila Bend VOR to Saddle intersection. When you reach Saddle intersection, you'll turn east and proceed inbound on the 256-degree radial of the Willie VOR. From over Arlen, you can expect radar vectors to the final approach course if runway 8 is in use. If runway 26 is being used, you should expect radar vectors prior to reaching Tukey intersection. Now that you've reviewed the arrival procedure and set the radios and navigation equipment, you can begin to plan for the approach. Tune in and listen to the ATIS broadcast to get the current weather and information about the approaches in use and the landing runways.
Wind 070 at 8, altimeter 299er2, ILS runway 8 right approach in use, landing runway 8 right. Advise Phoenix approach control, you have information Romeo.
With this information, you can now review the specific approach chart and determine the frequencies, inbound course, descent and landing minimums, missed approach point, and the missed approach procedure. It's important to review these early in the arrival to reduce your workload later. Just before you reach Hyder intersection, Phoenix approach issues the following clearance.
Cessna 241, cross Paint intersection at 10,000.
This clearance authorizes you to begin the descent to 10,000 feet at your discretion, as long as you are at 10,000 feet when you pass Paint intersection. To comply with the crossing restriction, you must determine when to start the descent. Since your present altitude is 12,000, you'll need to lose 2,000 feet. Assuming a 500 foot per minute rate of descent, it will take 4 minutes to reach 10,000 feet. A 4-minute descent at a ground speed of 120 knots will cover 8 nautical miles. The distance from Hyder intersection to Paint intersection is 11 nautical miles. Therefore, if you begin your descent after you pass Hyder, you should be at 10,000 feet, approximately 3 miles before Paint. From Paint, it's another 8 nautical miles to Arlen, where you can expect radar vectors off the arrival to begin your approach. A descend via clearance simply instructs you to follow the altitudes published on the star. If you were instructed to descend via the Blythe 2 arrival, you would be expected to stay above the MEAs published on this chart. If ATC amends your route or altitude to something different than what is published on the star, it effectively cancels the procedure and places you on radar vectors. Arrival procedures make the transition from en route to approach an easy and orderly procedure for both you and ATC. The specifics of an instrument approach, such as altitudes, headings, descent angles, and missed approach procedures, may vary widely from one airport to another. Understanding the fundamental elements of an approach allows you to effectively plan and execute individual charted procedures. Your planning should begin with the pre-flight review of the approach procedures for your destination, and, if applicable, the alternate airport. This will ease some of your workload later when flying the approach. Your in-flight review typically begins as you near your destination. The type of approach to expect is provided by a controller or is broadcast on ATIS.
Warrior 147, turn right heading 160, maintain 3,500, expect ILS runway 19er left.
Roger. Warrior 147, turning right to 160, maintaining 3,500. We'll expect ILS runway 19er left.
Now that you know which approach to expect, you can concentrate your in-flight review on the specific chart. Briefing strip charts provide an easy way to quickly identify the primary items during this chart review. Make sure you have the correct chart by verifying that the heading matches the procedure you're about to fly. Use the communications row to review and set the necessary frequencies you'll use throughout the approach. Use the information in the next set of rows to tune and identify the primary navigation aid, and to review the final approach course, the appropriate altitudes, and the missed approach procedure. Also check the procedural and equipment notes, and the MSA information. Next, you'll want to review the plan view to familiarize yourself with the procedural tracks, nav aids, and headings. The profile view shows the appropriate altitudes for the approach, as well as the headings and fixes along the approach course. Check the conversion table to determine descent rate information. Also, note the appropriate time to the missed approach point in case you must fly a localizer approach due to an equipment malfunction. In this section, review the approach lighting so you know what to expect when you see the runway environment. Should a missed approach become necessary, this portion of the chart provides a quick reference to the initial up and out maneuver. Finally, review the minimum section to determine the minimum altitude and visibility for the approach. The pre-flight and in-flight review of the approach helps to reduce your workload during the actual approach. It also reinforces where to find the information quickly if needed. Now let's take a look at some of the common procedures used to fly an approach. One of these is the use of radar vectors to align your aircraft with the final approach course.
Phoenix approach, Cessna 241, leaving 12,000 for 10,000.
Cessna 241, report Arlen.
Phoenix approach, Cessna 241 at Arlen.
Cessna 241, turn left heading 055, maintain 5,000 until established on the localizer. Cleared for the ILS runway 7 left approach. Contact Phoenix Tower at Reno on 120.9er.
This clearance includes 4 key elements. They are the assigned heading, the assigned altitude, a clearance for the approach, and the instructions for when to change frequencies. Normally, the final heading assignment allows you to intercept the final approach course in sufficient time to establish yourself on the course prior to the final approach fix. Maintaining the altitude assigned by the controller is very important. Controllers assign altitudes that are at or above the minimum vectoring altitude, which provides both obstacle and terrain clearance. Do not descend from this altitude until you are established on the final approach course. Your clearance for the approach means you are expected to intercept the final approach course and fly the approach as charted without a further clearance. However, at a tower-controlled airport, this is not a clearance to land from the approach. Now let's turn our attention to some of the unique aspects of non-radar approach procedures. Without radar assistance, you must follow the charted procedure to align the aircraft with the final approach course. In some cases, your direction of arrival allows you to intercept the final approach course and proceed with a straight-in approach. When this occurs, the chart indicates no PT along the route. At other times, you must execute a procedure turn or course reversal to align your aircraft with the final approach course. The most common procedure turn depicted on approach charts is the one shown here. When this symbol is shown, the method you choose for the course reversal is optional. However, no matter what procedure you use, you must remain within the protected airspace allotted for the procedure and fly the reversal on the same side of the course as it is charted. The method of course reversal for some procedure turns is not optional. When a procedural track is charted, such as this teardrop or this holding pattern, you must fly the procedure exactly as shown. Another important aspect of an instrument approach procedure is whether you can make a straight-in landing or whether you must circle to land. If a circling maneuver is required to align the aircraft with the active runway, there are several issues you must keep in mind. First, you need to know which category you will use for the approach. Remember, if you use a higher than normal approach speed, you must use the minimums for the higher category. Using the appropriate category will ensure you remain within the protected obstacle clearance area defined by the FAA. For example, the protected area for a Category A aircraft is a 1.3 nautical mile arc measured from the end of each usable runway. It also includes the tangent areas. The area for Category B aircraft extends out to 1.5 nautical miles. The obstacle clearance area for Category C aircraft extends out to 1.7 nautical miles. And Category D arcs extend to 2.3 nautical miles from the end of each usable runway. The base of each area is the circling minimum descent altitude specified on the approach chart. So you can see that it's very important not only to maintain the minimum altitude while circling, but also to stay within the protected area for your category of aircraft. Do not descend from the MDA until you have the runway environment in sight and your airplane is properly positioned to make a normal descent to the landing runway. Another unique feature of every instrument approach is the missed approach procedure. It is carefully designed to provide adequate obstacle clearance throughout the segment. Although limited visibility is the primary cause of most missed approaches, you can initiate the procedure for a number of reasons, such as not being properly aligned with the approach course, or receiving specific instructions from ATC.
Cessna 241, execute missed approach. We have a disabled aircraft on the runway.
Beginning a missed approach before you have arrived at the MAP requires special consideration. For example, let's assume you decide to execute the missed approach between the VOR and the 2.8 DME fix. The charted missed approach procedure calls for a straight-ahead climb to 2,100 feet, then a left turn direct to the Mount Vernon VOR, followed by a hold. However, the missed approach segment does not begin until the missed approach point. Therefore, you must delay the turn until you reach the MAP. There is no restriction on climbing early, but an early turn may not provide the necessary obstacle clearance. Another situation that requires special attention is a missed approach during a circle-to-land maneuver. If you lose sight of the runway during a circling maneuver, the AIM recommends that you make an initial climbing turn toward the landing runway. Once you've landed, you must make sure your IFR flight plan is closed. At an airport with an operating control tower, your flight plan is automatically closed for you. At airports without an operating control tower, you must close your flight plan either by radio contact or through a phone call to the nearest flight service station or ATC facility. The foundation for instrument approach procedures comes from the Federal Aviation Regulations and other official FAA documents, such as the Aeronautical Information Manual. It's important to study these sources frequently to keep the procedural side of your IFR skills in top shape.